Good morning.
Hi, Julian.
How you doing?
Fine.
Good. Yeah. Pretty good.
Be here this morning to welcome you for this, which number is it? 35th, 35th colloquium of IAP. It's a great pleasure to be here, as I said, as a director of IAP, but also as a member and of the Euclid Consortium. As you may know, IAP is a laboratory of Sorbonne University and CNRS. We host here research groups of various interests, ranging from extrasolar planets, searches, galaxy evolution, high-energy astrophysics, theoretical physics, and of course cosmology, whether it's observational or theoretical cosmology, and involvement in many projects, whether it's from ground observation, from space, and two major projects of IAP, of course, Planck and Euclid. So you may know. Most of you probably know that we organize each year such an international symposium, and its topic is decided by the scientific committee of IAP. So here you have a list of the previous ones. So the last one for Planck was in like 5 years ago now, so I guess it was time to have another meeting, and that would somehow summarize what the greatest results of Planck, but also give a kind of a way to for Euclid. So it was quite natural for the committee at IAP, given the fact that this year we have the latest result of Planck, and that the preparation of Euclid is now in full development, that we had a conference dedicated to both this Planck and Euclid, and particularly, I guess, for IAP. And it is probably fair to say that Planck has set the stage for all the future developments of cosmology. Its science legacy is immense, whether it's for the matter or energy content of the universe, the physics of the early universe, ionization, and so on. Among other things, it confirmed that that the universe underwent a phase of accelerated expansion, but also a phase which is needed. Such an accelerated expansion which is needed for the late time evolution of the universe. As we all know, this is a dark energy issue, and this is precisely what Euclid is supposed to address. And so, but the legacy of science is not only about science or cosmological paradigms, it's also lessons to learn from the, I would say, organization, management point of view, how to deal with such a big consortia. What is at stake in both cases is to harness the full the full statistical power of the observations we have. Both missions are basically full sky observation of the sky, and what we need to do is to uncover cosmological constraints from the detailed behavior of statistical quantities, such as power spectra and so on. And in all cases, I guess end-to-end modeling of the missions is a key to the success. So, having said that, there are differences, and we will uncover them, I guess, during during this week. So this is anyway a very exciting time for exchanges, on experience, on methodology, on science objectives, on modeling of these observations, and for such a rapidly evolving domain of research. So that's it. I wish us a very fruitful conference. And so, please.
So hello everybody, it's really a great pleasure to welcome you to IAP. I will be very short because what I wanted to say, actually Francis covered it all. I will just say that the idea of this conference, as Francis said, started coming up last year. This year, we really thought it was the right year to have a conference on cosmology. Planck is finishing. We are waiting for Euclid to come in a couple of years. So the time is right, the place is right, IAP being one of the major players in Planck and also in Euclid. And when we talked with Francois last year, we really thought that the main point that we wanted to stress and the focus we wanted to put on was on challenges. So we wanted to, first of all, stop and see what's our understanding of the universe today as given by Planck and all the beautiful experiments that are currently taking data, or the very recent ones, and also a little bit highlight the new questions, not only the old classical questions that are in the field, but also really stress what are the new intriguing mysteries that these experiments have opened, and how are we going to solve these mysteries with the future data. I think clearly, for example, about the H-naught tension. Is this real? Is this going to teach us something new about the universe? It's just, opening exciting times. And the name of the game, we feel, for the upcoming and future experiments, as said, are systematics. And so we wanted really this conference to be around the challenges, the hard parts that we need to solve in order to have robust results. And I'll leave the word to Francois as well.
So again, my personal welcome to all of you. Many of you are friends for a very long time, and also a substantial part of the audience has been coming to this very amphitheater for a very, very long time and during the Planck years. Actually, it's a great time for me because after 27 years on Planck, we are finally really seeing the end, at least the official end, even though, as you will discover, there are still a few things lingering and a few challenges that we're trying to meet regarding simulations. But anyway, after literally hundreds of meetings in this amphitheater, as well as the Planck room and so on, I mean, this is a great relief to finally be able to hand over to the next generation. As was said, I mean, we were not prepared really 25 years ago to deal with such an experiment, and that was, as Francis alluded to, for astrophysicists, this is even more of a shock than for particle physics, having to deal with essentially herding a few hundred cats, not being prepared, being scientists. I had no training into management, into the novlang of agencies, of projects, which is like a whole different world, which unfortunately we have to cope with. But anyway, now one thing that we thought was especially timely is that I can sort of see the evolution of the community going into work in sort of silos, meaning that we are increasingly structured by big collaborations. And they are, as this is the nature of the game, they tend to be competitive with each other. Which means that some of the dirty laundry, which is actually very useful, is actually not exposed. And that's a problem as a community. Because, I mean, some of the hardest, I mean, you know, you get the sales speech in conferences. I mean, that we do all the time for agencies, for money, for all kinds of things. But in practice, a lot of the preparation and for success is actually within collaboration, and there is some uneasiness to sort of say, well, you know, I mean, there is this problem. We don't really know how to deal really with, say, you know, photoses. Just as a random example. Just not for Planck. No, not for Planck. But I mean, I'm trying to also put it into the future. I mean, and so I think the hope there is that we'll not be too much into sales speech, but a lot more about uncovering the dirty laundry and sort of be open about the problems we are trying to solve. Because I mean, competition is good, but we're trying to solve the same problems. Because in the end, cosmology means big data, co-adding a lot of data, ending with correlated results massively. Really, we're talking of having correlated variables which are in the millions now. So you just know if you're just brutal, I mean, this is million square determinants, all of these kind of things. So that's one thing that we have to face. Another thing that we have to face is the issue of how we communicate the real uncertainties which come from systematics. And, well, the only answer so far is to be able to do faithful simulations that encapsulate all the knowledge of the team. Well, that brings problems of its own, which are typically how you describe the instrument properly, how you find the resources, numerical and in software, to actually do this. And then maybe worst of it is the management. So in short, well, hardware is hard, software is harder, and people is hardest. And I'm talking from personal experience here. So that's what we'll be, I hope we'll be doing. And the agenda, I hope, that we spend a lot of time with Sylvia and the scientific organizing committee to structure this meeting so that this will be apparent. So Planck in itself is actually, the core of it is actually pretty short. This is his first session. Will be, we co-led with Martin the scientific legacy paper, and he will be describing to you in short so that we, as a setting stage, and of course Jan Tauber has been with us as the ESA scientific, well, whatever, coordinator or whatever, I forgot. After 25 years, this is being blurred. But he has also things to say about the difficulties that big experiments face. And so that's, but the rest of the week is really about taking stock of where we are. That is, well, current experiments and so on. And then moving to the future to get the challenges as far as we move forward in time to, well, essentially now to Euclid days. And so that's it. We hope to cover pretty much all of the most exciting proposals and collaboration work ongoing, again, with a twist towards problem solving and not so much about sales speech. I mean, that's really something we instructed all speakers individually, but for all of those which are still have time, haven't fully prepared their slides, which may happen, remember about the idea is really sales speech we hear all the time, and I can't care less. Now, on this, I want to conclude on this, sort of saying that we're going to have a lot of hot topics during this week. You're going to hear a lot also about cool stuff. And to top it all, there will be pretty hot weather coming, so please keep your cool. And on this, I think I'm pretty much done on Sylvia. Maybe you want to.
Yeah, so I'll just go with practicalities a little bit. So Francois explained you a little bit the program. We will have normal talks. We will have a few sessions with flash talks. So a part of the people that brought the poster have a 2-minute flash talk to present it. Poster sessions will be every day from Monday to Thursday. We have 2 rounds, so Monday and Tuesday, the first half of the posters, and then Wednesday and Thursday, the second one. It's in the afternoon. The afternoon coffee break is 1 hour to let you go and see the posters which are downstairs. So it should be easy. We've put so many signs for the poster room that I hope you will not get lost. That room is also available if you want to follow the conference from there. We are broadcasting the conference there as well. If you arrive late, whatever, and you cannot enter this room, you can follow the talks there as well. There is AC in the room, so if you feel that you really need to be cold. However, so for the moment there is no AC here. We did miracles on Friday, in particular Francois, and also the technical staff here at IAP. AC is coming this afternoon in this room. So we hope that for the hottest moments of the week, we are going to have some freshness. And in general, yeah, the conference is live streamed on YouTube, so you can find the link on the website. A few practical information. There is a room in the institute, but we have also Wi-Fi access if you want. If you are giving a talk, we really encourage you to use the laptop here, so to upload your talks to the link that we sent around on Friday. And in any case, please check that your talks work at the coffee breaks or lunch breaks. The institute, very important, the institute is open from 8 a.m. to 8 p.m. Outside these hours, you cannot leave the building. So you get stuck in actually between the building and the outer door. So please leave the building before then, and always wear your badge in the institute.
There might be an exception tonight.
Yes. Yeah, we're not gonna keep you here tonight. Poster session, we said, and the lunch is not provided, but there are plenty of places. There is Rue Daguerre, which is just on the other side of the Place d'Enfer Rochereau, and you have a lot of options there. And these are the social events. So today we're going to have the cocktail between 6:30 and 9:30. Tomorrow we will have the conference picture in the afternoon during the coffee break. And on Thursday we have the conference dinner in a very nice restaurant in Parc Montsouris, which is in a park. 7:30 for the aperitif, and then the dinner is at 8. And yeah, smart casual clothing dress code. We are all.
Are you proposing a short trouser for those who don't have them?
We are just, it's a nice restaurant, so you don't have to dress up, but yeah. Again, please bring your badge there so we can check that you are from the conference, and you should have like a little card if you had like meal requirements in the back to show. And on Friday, we have the pleasure and honor to host the Gruber Prize ceremony, which the Gruber Prize is going to Joe Silk and Nick Kaiser this year. And the ceremony will happen after the conclusions of the conference. So between 5 and 5:30, we're going to have a break, and then 5:30, the ceremony will take place. We will reserve some seats to the Gruber guests, so please leave those seats free, but for the rest, you are very welcome to join. And after that, you are very welcome to join the cocktail after the ceremony. You can reserve taxis if you need at the reception every day before 3:30 in the afternoon. And if you need anything, you can contact any of the LOC, myself, Francois, Karim, who is sitting here, the guy in shorts, Eric, who is there, Shivadip, who is not in the room, probably taking care of the posters, and Sandy and Valerie, who are the admins that you met this morning. And something that we would like to say also is that this conference has a code of conduct, so we really would like this conference to be, enjoyable and productive for everybody. So discrimination and harassment is not tolerated. So if you have any problem, please come to us. And I guess that's it. Have a great conference, everybody.
You are equipped, yeah.
Yep.
Yes.
Yeah, I forgot. Be on time because.
Yeah, beware of Wendy.
Okay, well, thank you very much. I was asked to give an overview of the cosmological legacy of Planck. Now, of course, when you have such a large and talented team working on an amazing data set for as long as Francois intimated we did, there's just way too many results that I could possibly cover in any finite amount of time. So I've tried to be kind of brutal and hit just a few highlights of the cosmological legacy, and I'm sure we'll hear more about that as the conference proceeds. But I thought I'd start the story with this map of the temperature anisotropies in the cosmic microwave background, because this can stand in as a proxy for really where most of our cosmological analysis, most of our cosmological information comes from. Now, the slide projector itself, of course, doesn't do justice to the map. You can't really see the tremendous angular resolution and dynamic range that the Planck data are capable of. On the other hand, you definitely get an impressionistic view that there's an awful lot of structure on a variety of different scales and a lot of information really on the CMB anisotropies across the whole sky. Now, the presentation problem becomes much, much worse when you go to polarization. A lot of the information in Planck does come from polarization, but it's very difficult to show. So here we've smoothed both the temperature and polarization maps on 5 degrees, right? So much, much worse than the native resolution of the data itself. On the other hand, you can actually see visually here that we have polarized little sticks that have quite a large degree of structure that is partly but not fully correlated with the temperature. So if you have a cosmologist and you give them essentially anything, including a map, the first thing they'll do is they'll take its Fourier transform and try and compute a power spectrum. This turns out not to work particularly well for cats. On the other hand, for the cosmic microwave background, it's an exceptionally good approximation because the microwave background is very, very close to Gaussian, and therefore almost all of the information is contained in the power spectrum itself. So if we look at the Planck power spectrum, that's here as the data points. You can see exceptionally good measurements of the cosmic microwave background power spectrum all the way out into the damping tail through many, many, many acoustic peaks, out into the point where the information really starts dribbling away. The data are shown as the red points here. The theoretical line, the blue line, I'll come back to in just a minute. We've measured not just the temperature, of course, but the polarization. And so here's a plot showing the temperature polarization cross-correlation spectrum, and you see qualitatively the same kind of behavior, spectacularly small error bars, a huge amount of structure that is extremely well fit by the blue line. And then finally, we can look at the autocorrelation of the polarization, and something that I'm going to come back and talk a lot about at the end of the talk, which is the power spectrum of the lensing of the cosmic microwave background. Now, in each case, there's this blue line that goes through the data points. That's the prediction of a lambda CDM model that has been fit simultaneously to all of the 4 spectra I just showed you. And as you can see, just visually, it also provides a good fit individually to each and every one of those data sets. And so one of the nice things about what we were able to do with the final data release of Planck is you can go and drop out any one of these spectra and basically get more or less exactly the same answer as we got from the other 3. So that's an amazingly good consistency check. Now, this blue line is perhaps one of the best examples I know of sort of physics-based data compression, right? Because we take trillions of bits of data that come off the satellite and we compress them down into billions of measurements on the sky. Those billions of measurements go through a process of template extraction to pull out the cosmic microwave background that gives us tens of millions of pixels or tens of millions of harmonic modes. We then compute the power spectrum from that to get thousands of multipoles in the power spectrum, and they're all fit by a 6-parameter cosmological model, right? So that's pretty damn spectacular. There's no evidence at all in the Planck data for a 7th cosmological parameter. Now, at every one of these stages, of course, you're focusing the signal to noise down onto the questions that you're in principle really interested in. And so for the base model, the cosmic microwave background determines all of the parameters simultaneously and on its own with exceptional accuracy. The best determined parameter is 0.03%, and of the 6 parameters, only one of them is now not determined simultaneously to better than 1%. So this shows you the 6 parameters in the standard cold dark matter model that we fit. There's a baryon density, a cold dark matter density, the overall angular size scale of the acoustic fluctuations. This is the one parameter that is not determined to better than 1%, the optical depth of Thomson scattering, which we're going to hear about in just a little while. And then you have the amplitude and slope of the primordial power spectrum. These points in red are all determined to better than 1%. And this thing is in orange because the claim that it's determined to better than 1% really rests on the convention that a scale invariant spectrum has n of 1 rather than, say, 0. So n less than 1 indicates a spectrum that has slightly more large-scale power compared to small-scale power when you compare that to a scale invariant spectrum. Now, these are the parameters we mostly deal with, but of course within the model you can then derive a large number of other parameters, and 2 of them that I'm sure we're going to be hearing a little bit about as the conference proceeds, as the expansion rate of the universe, or the Hubble parameter, which we get to be a number between 67 and 68 kilometers per second per megaparsec, and the amplitude of the fluctuations in the matter today, sigma 8, which we get a number to be about 0.81. Now, you can also derive a lot of other parameters. One of my favorites, and it'll come up a little bit later on in the talk, is the size of the horizon at matter radiation equality, which you can see Planck determines with a really quite satisfying number of zeros in the error bar, right? So this is a very well-determined parameter. Okay. Now, all of these data are fit by a model based on inflationary lambda cold dark matter, which I've just argued is a pretty damn fantastic phenomenological model, but it does, of course, raise a number of questions. The first thing to realize is that this model has withstood incredible increases in data quality over the last 35 or so years since it was first introduced. It feels now like it was kind of inevitable that the model would fit everything, but Planck actually produced a tremendous increase in the data quality and the shrinking of the error bars. So it was at least logically conceivable that a model which makes very definite predictions might not have gone through the data. In fact, that's not what happened. The model predictions for the anisotropy spectra were really quite specific, and the data had the good sense to lay on top of them. And so instead, we now have this situation where many extensions to the model are highly constrained. Now, the model does a good job of explaining the data, but it has very many puzzling contents. One of the things that we've learned from the Planck data is that there's an upper limit to the neutrino masses, which to order of magnitude is about 100 millielectron volts. We have terrestrial experiments that give us a lower limit to the neutrino mass, which is the same order of magnitude, about 100 millielectron volts. And so therefore we know that at least to one significant figure, the neutrino masses are 100 millielectron volts. And of course the puzzle here is that the natural mass scale for leptons like this is set by electroweak scale, which is 100 giga-electron volts, and we really don't understand the 12 order of magnitude discrepancy there. We also measure other contents, like we measure the baryon density in the cosmic microwave background really spectacularly well now. And one of my favorite examples of sort of the universality of physics is that the baryon density determined from Big Bang nucleosynthesis matches exceptionally closely with the baryon density determined from Planck. And that's a really interesting thing because in order to do this comparison, you basically need to invoke in the model all of the fundamental laws of physics. at the edge of the observable universe, right? And so this tells us that physics works in the early universe basically the same way as it does here in the lab, which is kind of amazing. We also measure the matter density, and one of the things that comes out immediately, of course, is that the baryon density and the matter density are not the same. And so in fact, that gives us evidence for the cold dark matter part of the lambda cold dark matter model. But another puzzling thing is that the baryon density is not orders of magnitude smaller than or larger than the matter density. So apparently these two parts, the baryon density and the matter density, come from very different sectors of the theory, but their abundance today is very, very similar, within a factor of 5 or so. The same thing happens with dark energy. One of the things we've learned from Planck is that dark energy turns on very, very rapidly today. We have exceptionally good constraints on early dark energy now from Planck. And so dark energy is very much a late time phenomena. And so this kind of is the why now problem, which has become incredibly sharpened with the Planck data. In addition to finding all of these things, of course, we also find lots of not things. So we don't see any extra relativistic species, we don't see any spatial curvature, and so on. So there's lots of directions the model could have chosen to go in that it didn't. So this model is amazing. It connects high-energy physics to cosmology and explains, in quotes, 14 gigayears of cosmic evolution. But our understanding of this model is, of course, highly incomplete. So now what I want to do is sort of bookend this 14 gigayears of cosmic expansion by talking a little bit about the very, very early universe and then turn to talking about the low redshift universe. So in terms of the very early universe, I want to talk about Planck and inflation. And even from the early 90s, the cosmic background quickly established that the perturbations that we see in the large-scale structure in the universe really came from a very, very early universe origin. And Planck has continued that inference. And everyone's favorite example of a model which produces perturbations in the early universe is probably inflation. And Planck has had quite a huge impact on inflationary model building. A large number of popular models, things like m squared, phi squared, lambda phi to the 4, and so on, are now ruled out quite definitively by the Planck data. On the other hand, Planck is in very good agreement with the inflationary paradigm or the inflationary idea. So the simplest models of inflation predict a spatially flat universe, and Planck gives us a measurement of that to within 0.2%, with a nearly scale invariant spectrum of density perturbations, but one that should depart from scale invariance, and roughly speaking, it should go in the red direction. We now have 8 sigma evidence that that is the case. It should be almost a power law, this primordial spectrum, and this is an area where Planck has really dramatically increased our confidence in that statement. So here's just an example. The running of the spectral index is very, very consistent with 0 over the entire range of the Planck data. It's dominated by scalar perturbations. Just from Planck alone, we know that's true to an order of magnitude. If we include other data, for example, from Bicep and Keck, it gets even stronger. The fluctuations are Gaussian. We know that to 5 10 to the minus 5, which is pretty Gaussian. They're adiabatic, meaning that an overdensity in dark matter is an overdensity in baryons, is an overdensity in photons, is an overdensity in neutrinos, and we know that also with very, very high confidence. And it has negligible topological defects, right? No monopoles or cosmic strings or something like that. Now, I'm not an inflation theorist, and I wasn't going to drag you through a long litany of inflationary models, but I wanted to give you sort of my takeaway of sort of the lessons for inflationary model builders that come out of the CMB data and Planck. So I already argued that the coherence of the peaks and the sign of this TE cross-correlation really argue for a very early universe origin to the perturbations. And I argued that most people interpret this within the context of slow roll inflation, and so I'm going to do the same thing. So this measurement, this observation that omega curvature is close to 0, basically tells me that the duration of that slow roll phase wasn't very finely tuned. The fact that this primordial P of k is well approximated by a power law tells me that the inflaton, whatever it may be, rolls down a relatively featureless, nearly flat potential. The fact that we don't see any isocurvature modes suggests that there's only one relevant degree of freedom at this important period during horizon exit. And the fact that scalar modes dominate by 1 order of magnitude is starting to put pressure on these models which have a tensor scalar ratio that's first order in the slow roll parameters, so in 1 minus ns. And Planck has already ruled out a number of those models, and we may see them be further constrained in the future. Unfortunately, Planck just doesn't have the sensitivity that's required in order to probe this next class of models in which R is quadratic in the slow roll parameters. That requires next generation technology. I'm sure we'll be hearing about that in the future. And then the class of models, of course, that have R much less than quadratic in the slow roll parameters, I think are just out of reach of anything that anyone's come up with any idea of how to do. Now, all inflationary models, of course, have some degree of fine-tuning to them. And roughly speaking, you can either be at a rather generic point on a very, very special potential, or you could be a very special point in a more generic potential. And I think what we're seeing is that surviving models tend to have V prime close to 0 and V prime V double prime much less than 0, and so you're close to a special point, you're close to a local maximum in the potential. Let me change gears now and talk about the low redshift universe, and in particular, the CMB lensing from Planck. So, photons from the CMB are deflected on the way to us by potentials due to large-scale structure. This is true of, photons traveling any potentials. And what this does is give a sensitivity to the low redshift universe directly within the Planck data itself. So that's nice because it allows us to break some degeneracies to do with geometry and late-time expansion from purely within the CMB data set, which is very, very nice. But it also provides a cross-check on the paradigm because we can ask whether the structures we see at low redshifts, 1, 2, 3, etc., are consistent with the initial conditions that we measure back at the surface of last scattering after a factor of 1,000 in growth. And what's quite remarkable is after these perturbations have grown by a factor of 1,000, we end up with a measurement of the amplitude in kind of units of the theoretical prediction that is within 3% of 1, which is really quite a strong test after a factor of 1,000 of growth. The other thing is, if you interpret this within general relativity, Planck provides a map over the whole sky of the projected mass back to the surface of last scattering, in the limit that the surface of last scattering is essentially all the way to the horizon, and that the 2/3 or so of the sky that's clear of the galaxy is the whole sky, we've basically made a map of all of the matter in the universe. Now it's in projection and at low resolution, but still it's a map of all of the matter in the universe, which is kind of cool. This shows you that map. The lensing signal is now measured at more than 40 sigma. This map shows you actually the deflection angle, which if you convert these units is about a few arc minutes, and you can see it's measured over much of the sky. Now, I really, really, really like this map because I think it's actually a first for lensing, but it's important to be clear what it's a first of, because Planck was certainly not the first experiment to measure gravitational lensing. That's like the twin quasar in 79 or something. It wasn't the first experiment to measure gravitational lensing by large-scale structure, and it wasn't the first experiment to measure gravitational lensing of the CMB by large-scale structure, and so at this point you're beginning to ask yourself, why on earth does it deserve the topic first at all? And the reason is that it was the first to do it over a significant fraction of the sky with enough signal to noise to really start driving the fits. So it's now providing quite a sharp test of the theory. Previously, lensing was consistent with measurements which were done much better by another way. But now it's actually quite competitive with many other measures. And so to me, this is like a coming-of-age story for CMB lensing. And the reason I like this is because I think much of the future of CMB will be CMB lensing. And Planck is going to usher in this new era of CMB studies, of this intermediate redshift universe. And one of the cool things from my point of view is that all of the CMB studies are going to be getting better at the same time as we're going to have much, much better optical and near-infrared data, right? So dark energy survey WISE, HSC, DESI, PFS, and then in particular LSST and Euclid, and maybe one day WFIRST. And so just to give you an example of that, this is the current situation when you cross-correlate galaxies in the low redshift universe with Planck CMB maps. This is some work done at Berkeley by Alex Kralewski, Simano Ferraro, and company. This shows you the autocorrelation of WISE galaxies at redshift 0.5, 1, and 1.5, but the panel I want to focus on is these down here, which show you the cross-correlation with the Planck lensing maps, which you can see are measured at tens of sigma, each roughly independently. And so the interesting thing is, if you dramatically improve the CMB maps and you dramatically improve the optical maps, you can actually push this over essentially the entire age of the universe. So this shows you the redshift distribution of a variety of different traces. These are galaxies in magnitude-limited bins running from 20th through 30th magnitude. Some of the sort of stand-ins here for LSST year 1, LSST year 10, DES, and DES deep. These shows you, for example, the DESI ELGs and the Bose quasars. And then these bumps here show you Lyman break dropout galaxies that you can select in, say, LSST data out to extremely high redshift, out to redshifts of 6 or so when you start losing things due to the epoch of reionization. And this gray band basically shows you the lensing kernel, the strength of the lensing from CMB lensing. Now, if you run through the numbers with something like LSST or Euclid or one of these other futuristic surveys, you can measure in cross-correlation the lensing against every one of these galaxy samples with hundreds of sigma, sometimes approaching 400 or 500 sigma, if you have a large enough sky map with enough signal to noise in the lensing. And so measure the shape and amplitude of the power spectrum over essentially all of cosmic history. So this is a dramatic increase in the volume over what we can do at redshift less than 1, and it will allow us to basically probe 10 or 11 gigayears of 14 gigayears of cosmic history. So that's quite an amazing possibility. But the connection between the CMB and large-scale structure is actually even deeper than that. Roughly speaking, by studying the CMB, we really cemented this gravitational instability problem. No one really talks about superconducting cosmic strings as the answer to structure formation anymore. We've also measured the initial conditions and the parameters that govern the late-time evolution. And so Planck really sets the entire framework for large-scale structure. When people talk about large-scale structure surveys, it's kind of a given that you mean plus Planck. And Planck precisely determines many of the key parameters for large-scale structure. So this number we've seen before, this is the horizon size at matter radiation equality. That sets the shape of the matter power spectrum. Sigma 8 at redshift 2, around about the peak of the lensing kernel, is known extraordinarily well, and so that sets the amplitude of the fluctuations in large-scale structure. And so we're very used to talking about standard candles or standard rulers, but Planck actually provides a standard fluctuation spectrum, which has been calibrated at percent level or sub-percent level. And in fact, this sets the scale and level of inhomogeneity in the entire universe. So this governs all of structure formation, all of galaxy formation. If you want to say whether your galaxy survey is a fair sample of the universe, whether it's dense or whether it's sparse, if you want to work out the number of dark matter halos you have per unit volume or any of those things, it all basically comes from this spectrum. And if I'm allowed just a brief sociological note, early on, the fields of large-scale structure and CMB were very tightly coupled. It was more or less the same theorists who were doing the same work. But, as often happens with fields, they grew apart, they specialized, they developed lots of their own techniques and their language. I think what we're seeing here is a science-driven recoupling of these fields. I think that's going to be really, really valuable because they've been apart long enough that they can learn a lot from each other, but they have enough in common that I think that it's relatively easy to make that cross-fertilization. So just to kind of illustrate this, I want to show you a sort of a big picture plot from the Planck Legacy paper, which I happen to really, really like. So what's plotted here is the linear theory dark matter power spectrum at redshift 0 as the black line. And then a whole series of data points where what we've done is we've taken the data and using the model, we've interpreted them as measurements of this linear theory dark matter power spectrum evolved to redshift 0. Now, what I want to pull out of this is not necessarily, how well these points lay on the line, although that's kind of cool, but the fact that I can do this at all tells me that I have an extraordinarily predictive model, right? Because this model is able to interpret observations of the CMB, observations of galaxy cosmic shear, observations of galaxy clustering, and observations of the intergalactic medium, and it's able to do that interpretation from megaparsec scales to the horizon and from redshift 1000 down to redshift 0. So this predicts an awful lot and gives us a framework for making lots of different comparisons. If we didn't have a model like this, there would be no way to talk about the tensions between all of these different data sets, right? So this is an important point. But of course, in modern cosmology, if I show you a log-log plot, I've probably hidden 1,000 sigma worth of discrepancy. So to really see science from this, we have to zoom in. This shows you one example of some of the inferences we can make, this one on the cosmic distance scale, so the background cosmology. This lower left plot shows you measurements of the distance scale as a function of redshift from baryon acoustic oscillations, where the gray line is the lambda CDM prediction conditioned on the Planck data. And what you can see is kind of percent level agreement with these lower redshift distance measurements with a sort of 2 and a bit sigma detention at redshifts 2.5. If I focus on these 3 boss points here, which have the tightest error bars, this shows you those blown up into distances transverse to the line of sight and along the line of sight. So you've got the 68 and 95% confidence levels at redshifts 0.4, 0.5, and 0.6. And again, this little error bar here shows you the lambda CDM prediction conditioned on Planck. It's actually kind of interesting. If you look at this, the temperature data tend to lie out here on the right. And then if you add polarization or you add lensing or you add BAO, each and every one of those pushes you in the same direction, which is to slightly lower omega m and slightly higher h naught, which is kind of an interesting result. So if there happened to be a fluctuation, it's probably with the most outlying one, which would be the temperature. So that's worth bearing in mind. However, these are all perfectly consistent with each other, and so if you just throw them all in, you end up with this amazing 0.2% constraint on the curvature of spatial surfaces in the Friedmann model, which is an amazing, amazing result. That comes from subtle features in the shape of the matter power spectrum. We can also look at the amplitude of the power spectrum and how the amplitude of the power spectrum evolves. And again, these tiny little error ellipses here show you the inferences from lambda CDM conditioned on Planck, and then these show you the 68 and 95% confidence levels from direct measurements in the galaxy distribution at redshifts 0.4, 0.5, and 0.6. Okay, so I'm rapidly running out of time, but I wanted to take a little bit of time to talk about something that may not actually be all that scientifically deep, but it's just plain cool. So every year we published a kind of a silly thing as part of the Planck papers, partly to keep us sane. So in 2013, Planck detected the motion of Planck, but Planck was going around the sun with the Earth. So let's call it the motion of the Earth in the aberration of the measured CMB anisotropy. Now, I think we kind of knew that the satellite was orbiting the sun. That was sort of the point. But still, to see this in the data, if you stop and think about, why would anyone bother to do this apart from too many Planck meetings, it's because we have a 10 to the minus 3 aberration on a 10 to the minus 5 signal that has to be stable over a year as we go around the sun. I think that's the right kind of scale for going around the sun. And so that means you need kind of parts per billion stability over 10 to the 7 seconds or something. That's actually quite challenging. And so the fact that you can pull this out of the data is sort of a testament to the incredible stability of the instrument. Plus, we proved the Earth moves. In 2015, we detected not just the impact of not just the impact of the 2 Kelvin neutrino background, but we measured the anisotropy in the neutrino background at 10 to the minus 5. Not that anyone doubted that neutrinos feel gravity, but still, this is kind of an amazing thing. And we've now measured that at the kind of like 5-ish sigma level, 10-ish sigma level. And so we have exquisite detection of the free streaming of the neutrino component in the early universe, right? Now, again, we kind of knew that neutrinos don't interact much and move close to the speed of light, so this wasn't a huge shock, but it's incredibly cool that you can do that 300,000 years after the Big Bang. And so, to top it all off, in 2018, we measured the gravitational slip at redshift 1000. So what is the gravitational slip? Just to remind you of your general relativity, if you think, for example, of the bending of light around the sun as measured in the Eddington eclipse expedition, right? You'll remember that the sun produces a gravitational field, but it also bends space. And in general relativity, you get kind of 1 unit of space bending for every unit of gravitational potential, and that's why the bending of light is twice as big as your naive prediction would have it be. And so this ratio of the bending of space to the gravitational potential is known as gravitational slip, and it's normalized to be 1 in general relativity. And so we've actually measured the gravitational slip at redshift 1000, because we have photons and we have gravity, right? We've measured that gravitational slip to be within 1% of the GR value. Again, not that anyone actually doubted that GR worked at redshift 1000. After all, we're doing cosmology here and so on. But still, it's amazing that you can make a sub-percent level measurement all the way at the edge of the observable universe, right? So it's an amazing thing. OK, so let me wrap up. Planck has essentially completed this primary temperature anisotropy story that was begun back in 1992 by Kobe. We've extracted almost all of the physics you can get out of the temperature spectrum. And we've established, along with baryon acoustic oscillations, this sort of acoustic physics as really a gold standard probe of cosmology. Along the way, we've impressively confirmed the standard cosmological model, which is something starting to feel as though this is kind of, God-ordained or something, but it was not obvious in advance that was going to work. We've provided precise constraints on the model and on the parameters, very tight limits on the deviations from the base model. There's some indications of both internal and external tensions, and I'm sure we're going to talk about that as the days proceed. But with only one exception, they're of relatively modest statistical significance. And that one exception, of course, is a high significance measurement of the Hubble constant at low redshift by one group. I think we've started to establish CMB lensing as an actually competitive cosmological tool, something that makes measurements that are as good as other people are making it. And for me, these synergies between large-scale structure and the CMB are only going to grow in importance, especially as we go into this next generation, where both the CMB missions and our ability to probe large-scale structure are going to be dramatically improved. And so in the next decade, we're going to see a host of new facilities coming online, and they're going to enable very, very precise tests of our models, hopefully turn up something new, but they're all going to build upon the cosmological legacy of Planck. Thank you.
Thank you very much, Martin. Questions?
Exactly.
Which then should lead to a slight difference of the two gravitational potentials.
That's right. We have, in fact, seen that, and we've seen that with high significance. When I said it was in units of the GR prediction, it was specifically taking into account the anisotropic stress at high redshift. So what we did is we defined it to be sort of phi minus eta psi was given by the anisotropic stress. And so we just normalized it so that the slip we measured was in units of the GR prediction, right, which in the low redshift universe is the two are equal, but in the high redshift universe, as you point out, is that they are not equal, they differ by a very specific amount.
Joe.
So you made the excellent point that 6 parameters give a wonderful fit, and there's no evidence for, to mention 2 more, curvature or excess numbers of rotating species. However, we do know also that if you add more and more parameters, including one or both of these, that the tensions, the biggest tension we have at the moment, does get reduced. Now, it doesn't go away, but do you think that's a possible indication that we may be a little premature in dismissing these other?
No, if I read my statistics book, no. I mean, if you keep adding parameters, obviously the constraints get weaker, and the tensions therefore weaken in terms of number of sigma. But I don't see any drastic shifts towards the preferred values from other experiments, which is what you'd like to see, right? I add an extra parameter, and it's not just that the error bars blow up, but everything stays more or less the same. It's that you see a huge shift towards what the other guy is measuring.
Well, they do shift in the direction that those
a little bit.
are partially reconciled.
Yeah. So you really need to be adding 2 or 3 parameters to start reducing this down to a, I don't know, acceptable level of agreement. And I think also, I haven't seen any of these models which were designed, which solve someone else's problem as well, rather than just being designed to solve ours, right? I'm always happier if you have to introduce fewer tooth fairies than things you're trying to fit. And I don't actually feel that's the way that things are going right now. On the other hand, the universe is not good at listening to my opinions, I've noticed over time. So we are going to test every one of these extensions with future data. And we don't have to philosophize, I don't have to philosophize over whether these tensions are or not, right? I think some of these methods for for changing the expansion history at high redshift, for example, which may explain the Hubble tension, they will be exquisitely tested by upcoming CMB data and so on. So I think this is a situation, let's wait and see what the further data says.
You mentioned the future CMB lensing measurements. People can't hear them.
Yeah, thank you. You mentioned the future CMB lensing measurements done in cross-correlation with different galaxy samples. Can you explain how much our understanding of the biasing properties of these galaxies will be a limiting factor?
Yeah, it's certainly not a trivial thing. One of the really nice things about CMB lensing, as distinct from, say, cosmic shear, is you're forced to work on large scales, right? Because you kind of run out of oomph on small scales. And as you go to higher redshift, the universe becomes more perturbative. Right? And so a perturbation theory-based analysis actually becomes quite applicable. And if you do one of these kind of symmetries-based biased expansions, it turns out that you can fit out to essentially where you run out of signal-to-noise in the lensing with 4 or 5 parameters, maybe 3 parameters if you're lucky. It's better if you can go to lower bias samples than if if you're working with very, very bright samples. But when we've looked at this, we've been able to get percent level fits well out into L's of several thousands with a small number of parameters, with no sign when we do this with HOD models and simulations and stuff. No sign that anything funny is happening. So I think that we're actually in much better shape than trying to work to say L of 5,000 in the low redshift universe, for Euclid or for LSST or something. And our photometric redshifts are really good.
So talking about dirty laundry, which of the aspects of the Planck mission are you still most worried about, or which of the internal tensions are you taking most seriously?
I guess that there's a separate answer to both of those things. I am worried about the tau measurement. I don't know that there's anything wrong, but the history of tau measurements from the CMB has not painted us a very confident story, right? 0.17 all the way down to 0.05 over time. So I guess I'm still worried about that. That's a really hard measurement. It was pushing the limits of everything. It's also an incredibly important measurement, and so otherwise I wouldn't really worry about it. In terms of the tensions, I don't know which one I'm most worried about. I think the situation as regards the amplitude of cosmic shear at kind of lowish redshift is very, very puzzling. But it's also evolving and not really settled. And so I'm kind of in this situation where I'm worried but not scared. I don't know exactly how to parse these things. So we'll see how that evolves. But I'm watching it closely for sure, because that's not making a lot of sense to me right now. With the Hubble constant, I have no ideas whatsoever. I don't quite know what to say. There's one measurement that's discrepant, and then there's a whole bunch of ways of doing it from a kind of theory-based approach that give the same answer. And so that either suggests that one measurement is wrong or the theory is wrong. And I don't see a problem with either, so I'm kind of stuck. Right?
Any more questions? Okay, we'll leave the tension there. Thank you, Martin. And next we have Jan Tauber on talking about the lessons learned from Planck.
So we're going to just pull it out. But I need the other adapter that Eric had. Okay, so good morning, everybody. This is going to be a very different talk from the beautiful one we just heard. To be honest, I wasn't exactly sure what the organizers were asking me to do. But on the other hand, my life was made kind of easy because some time ago, within the Planck teams, we did make a kind of intense effort to extract what we call lessons learned. And this was done by polling all of the players in the collaboration who had participated over the 20-whatever years history of the mission. And we wrote a document, as we often do. And that document is available, and you can download it. So the thing I want to say about this kind of effort is that, of course, you are always biased by your own circumstances. That is, you have a kind of, these blinders that horses have about what is important to your own experiment. And we often have an emphasis also on the negative aspects, so the things that didn't work well, rather than the things that worked well. And you should keep those two things in mind. Hopefully this applies to some experiments, and I think the ones that probably are most concerned by some of these lessons learned are those where, let's say, we're looking for very small signals in the face of important systematics. So hopefully that's something that may apply also to Euclid, and I think this is part of the intention of the organizers in asking me to speak about this. So this document has a very long index, and most of the chapters that you see in this index are actually about very specific technical issues. And so they are not necessarily applicable to most experiments. And therefore, I'm not going to talk about them here. I am going to talk about the last part of this document, which is more about data processing issues and maybe what you might call management. So I'm going to extract a few things which personally I thought would be of interest. It's all going to sound pretty vague and maybe obvious to most of you, but bear with me. I thought I would start by saying something about designing surveys. Obviously, there was a lot of discussion at the beginning of Planck of how you should do this, but there's one thing that we've learned on Planck is that null tests are fundamental. We use them for everything in the data processing chain. And what enables null tests is redundancy. You have to make many repeated observations. And as we know, the number of possible tests that you can construct increases dramatically with redundancy. It also increases your effort because you have to make these tests. But the benefit is huge from doing this. Now, just to remember that Planck, when we started out, the experiment was meant to live for only 6 months. We were going to do one survey of the whole sky. And then we kind of slipped in a second survey for redundancy purpose at the last minute, just before we went up for selection. We ended up doing 8. And that was really fundamental. And so the lesson I take out of here is that you really need high levels of redundancy. It's not a wish, it's a requirement. And I suppose that this will be built into experiments like Euclid. And that means time. You need long experiments. They are costly, I'm afraid. But I think that's an important aspect that needs to be designed in from the start. So, systematic effects. And Planck, at least for polarization, is limited by systematic effects, and certainly at large angular scales. The thing to know is that it's very hard to predict what's going to hit you in the real experiment. And the only way to try to beat that is to test on the ground as much as you can, and in as representative conditions. And I think we were somehow lucky because we were able to test Planck in close to representative conditions before we launched. But we really had to struggle to get enough time to test, because experimental conditions cost a lot of money and resources, and so you really have to fight for it, and that's an important element. In flight, you want to measure as much as you can, and I think here the lesson I have is not to underestimate the importance of what we call in the jargon commissioning and performance verification phases. They can be very long and complex, but you really need to do them because they will give you information that you need. Now, there's all kinds of systematic effects you can think about, and some of them may be quite tiny, or you may think they will be quite tiny, and so people tend to ignore them. But in fact, they may not be as tiny as you thought. And in any case, as you advance in data processing and you remove the bigger effects, the tiny ones will come up and will hit you. And so you really need to think even about the small effects in advance and how to deal with them. And of course, gathering as much data as you can. Again, what we call ancillary data, which is all the housekeeping information that you gather in flight, which may not necessarily be directly contributing to the science, but they will help you to understand the data. I think in some areas we didn't do well enough in Planck in that, and there is a lesson there to be ambitious. And then this one, okay, that's a bit vague, but when you start to get into very small systematic effects, you may have to change the whole way in which you process your data. And that means being ready to throw away pipelines. Now, more general things about data processing. What I'm trying to say with the top bullet is that there is a switch in your mind about doing science versus understanding the data. There are different things. And to understand the data, you need to use science as a guide, as a test. But the key is to try to understand what causes your data to behave as it does. It should not be the driver. Science should not be the driver because it will bias your results. And we were lucky in Planck to have a number of experimentally driven people in the lead of the mission, and that's really key because they're the guys who really want to understand the data. They may not necessarily be the best at doing the science, but they want to understand the data. And remember that as time advances and you deepen into the data processing, effects become subtler and more interconnected. You need to, you cannot separate problems into pieces and then solve them sequentially one at a time. You have to iterate through the loop or solve things simultaneously. For example, we learned that we have to do component separation at the same time as we do map making, which is not something we were doing at the beginning. So things become more difficult. We had a principle in Planck about keeping parallel pipelines, and that served us very well, but you have to keep a very good balance. At some point, we had 9 or 11 component separation methods that we were exploring, and that was really a big drain. It was really terrible. So you have to have a balanced approach there. But having at least 2 is really important. And I think in all of the main areas of Planck, we had at least 2 different pipelines trying to achieve the same results. Now, of course, the teams doing different things are competing, which is not always a good thing. But again, that's a kind of a management issue. Now, one important thing I find is that cross-comparing results from different pipelines is really difficult. If they are essentially doing the same thing, it's easy, but then it's not very useful to have parallel pipelines. So the usefulness comes when they are essentially somehow doing things differently, and then it becomes very difficult to compare results. So it's always good, and I think important to remember that it's nice to develop different pipelines, but you always have to think about what do you do at the end with the results, and how do you decide which one is the one that you want to use. Now, there's a lot of talk about blinding in big experiments, and I don't think we had this at the beginning in mind at all on Planck. My view is that blinding consists essentially of hiding some information from the experimenters to avoid experimenter bias. And therefore, in some sense, by the principle, it doesn't allow you to achieve the ultimate sensitivity, for which you need full information. So you have to be cautious about what you do, and not expect experiments like Planck to be able to actually implement blind approaches fully. But on the other hand, what is really important, I find, is that you should have full transparency. I mean, you can expose everything you've done, and you should release the data so that other people can criticize it and do it. And I think we've been fairly good at that on Planck, and I find it's unbelievable that there are still experiments that do not release their data. Yeah, that, I think, is a big sin. Now, I have here a remark about secondary science, but I mean, it's just a sociological issue. It can be a big drain of resources, and you have to spell out boundaries, how far you are going to go with that very early. Simulation, so invaluable, of course, and they are used for many different purposes. At least I think inside Planck, we did not have, from the beginning, we were not conscious of how important they would be. I wasn't, at least. Maybe other people were. And I think that we were barely able to produce enough simulations for our own needs. And I think the last 8 years, maybe, was being really driven by the need to do simulations. And I think compared to what future experiments are going to need to do, I mean, it's just, I think this is a huge challenge, and it needs to be thought through from the beginning. Of course, use of supercomputers requires specific experts, teams, not the same people who are going to do your pipelines. And so resources that are very expensive, that are hard to get time on, and need specific management to achieve the results. I think for an experiment like Euclid in particular, this is going to be one of the biggest issues that they will face. So of course, you're never alone in the experimental field, and there are other experiments doing similar things. Within Planck, I mean, LFI and HFI, the two instruments, were essentially independent experiments, and we could compare results to each other from these two instruments. But they were different at different sensitivities. They were sensitive to different systematics and so on. It is really difficult to compare results. And if you go to other experiments, it gets even worse. I mean, some of you may recall that when we published the 2013 data, we had a 2% calibration discrepancy with WMAP. And we worked rather closely with the WMAP team in full cooperative spirit, I would say, to try to track this down. And in the end, we were lucky in a sense because it was on our side that the problem lay rather than on the WMAP side, and we could track that down. But I think if it had been on the WMAP side, we would probably never have found it because the teams, although they were fully cooperating, you know, many of them had disappeared and they were not necessarily all that motivated to work on this. So it's you know, really difficult to compare properly your results to other experimental results. And then if you want to go further and incorporate results from other experiments into your own results, it gets even more difficult because you really need to understand those data. And I think what I take out of that is that you always have to make a clear distinction between what you can tell from your own experiment about the science and what you can tell with combined results. We flip-flopped a bit in Planck about that. In some cases, I think in 2013 and 2015, in 2015 we combined with other data, and then in 2018 we came back. Okay, this is more sociology, possibly collaboration aspects. It's clear that now very large scientific collaborations are becoming the norm. I think this was new for Planck, and certainly for astronomers to have such large collaborations. So we kind of learned on the go how to do that. I think the point I want to make in the next couple of slides is that this requires really a lot of management. It's a big overhead on resources, and you have to be willing to put that in. First of all, there's many different kinds of needs within the collaboration. Different people, different teams, they operate in different ways. This all needs to be managed. For me, the important thing here is that everybody has to know what's going on. Transparency is important. Flexibility. These are all scientists, no matter what they're doing. In fact, as you said, they are herding cats problem, but cats, they want to know what's going on around them, and you have to remember that. There's a lot of rules that need to be agreed. Secrecy seems to be fairly common in large collaborations. I'm not sure, I mean, how important it is for the actual results. It is important for creating a team spirit. And in that sense, I think it was useful, but again, it needs management. It needs people to be willing to do that. There's many other things you need to agree to within the collaboration, and that there's a lot of effort in forging this agreement. A lot of information flowing internally, which has to be actively managed, that cannot be left on its own. There's lots of meetings, reporting, information exchanges, and so on. All that needs, it's more than secretarial, I would say, but whatever. You need to have a schedule. And there's an important point here, I think, about producing internally data products within a collaboration that people can use to do science. You need to be very clear about that. That time scale can be very long. Within Planck, it took us several months at the beginning to go through the loop once and produce a set of products that people could think of using for science. At the end, it took much longer. I don't know, François, what you would say, but somewhere between 6 months and a year was kind of typical for going through the loop and producing something that people can use. This is long, and people people are waiting to write their papers, and so this is a big cause of stress.
You may recall that we went through 12 official internal release of products.
Well, in that case, it was less than 6 months, but okay. Rewards is very difficult, in particular for young scientists who are, let's say, the backbone of the science production, and they are the ones who have short time scales in principle, and they need the rewards, and that's something where I feel we did not do very well in Planck. That needs to be thought through, because otherwise these people will desert you, rightly so. And here's a warning about the last years of the collaboration. In my view, at least for Planck, they have been the most difficult ones. People are evaporating, they're going on to different experiments, you have fewer resources. Things get more difficult because the science is, you're scratching the bottom of the barrel. You need a lot more work, but you have fewer people and so on. These are the most difficult ones, and you should plan that into your overall schedules. Okay, data distribution. I'm not going to say too much about that. I think this is about delivering products both internally and externally. There's quite a lot of effort into actually validating products. You wouldn't believe how many simple mistakes are made in just producing FITS files and so on. And then, so validation, both scientific and physics. The big lesson for me in this overall thing is that all of the effort is put into writing scientific papers, but in fact, if you want to make products that are usable by the community, you need to put a lot of effort into explanatory documentation. It's not the same as writing papers, but it's maybe even more important than writing papers, because that's what people will look at when 5 years or 10 years after the experiment is over, they want to exploit your legacy. So writing and publishing papers, this is what people are there for. It's the reward. It's why they've been working many years. And so it causes a lot of stress and tensions. One particular problem, at least for Planck, but I think this is true of many large experiments and collaborations, is that you have hard deadlines to deliver data. And usually you're trying to produce a set of papers at the same time as you deliver the data. And so you have a lot of stress associated to these deadlines. This is an issue that, you're kind of forced into publishing papers before they've been externally refereed formally by a journal and so on, which is not the best practice. But you are forced to it because you can't just leave a data release deadline waiting for journal acceptance. And that forces you to have a very tight and thorough internal reviewing of papers. And I think in that sense we did pretty well in Planck. We've had very little trouble getting papers through external refereeing. I think our internal refereeing process was a lot tougher than the external refereeing process. So writing is key. It has to be planned. Internal reviewing, this is an important task. And by the way, it's a task that is very appropriate for senior scientists who are in the collaboration and may not have anything else to do in the collaboration. But it's very important. And no, I'm not meaning this. I don't mean this facetiously. It's really is important. They have an important task there. And the other thing is that, of course, these papers are collaboration papers, so everybody has to be somehow agreeing to what is in there. And actually, that's an important element to force you to be conservative. because you have to come in the end with a scientific message, which is the lowest common denominator, if you like, within the collaboration. So in Planck, we had an editorial board, and this was really an important element in the process of writing and publishing papers. And as I said before, it was a fairly large group of senior scientists, and they made sure that we were not making big statements that we might regret afterwards. And one interesting point is that it's good to make this editorial process quite independent from the final decision process to actually produce release papers or data. Keeps them independent. So public communications, I mean, this is public relations, if you like. Important. We know that cosmology is very attractive to the public. That's a big plus for experiments like Planck and will be for Euclid, I'm sure. I guess there's no need to say that one should beware of going out too fast with great discoveries, and I will not mention any names of experiments that have gone down that route. Public communications is a craft of its own. It needs experts. Scientists are not necessarily the best public communicators. Sometimes they are, but not always. And there are many parties involved, agencies, institutes, individuals. It all needs coordination. And I think the most crucial aspect for me is finding the right messages that you give to the public. And you know, professional communicators, they tend to be, of course, they want to give interesting stories, and so they are very bold. And scientists tend to be, at least in my Planck experience, tend to be very cautious. And there is a tension there, which is a good thing, because you find the right balance with the message. I remember we had a lot of discussions about how much weight to give to anomalies in the 2013 release. And in the end, I think we found a good balance. So I think I'm going to skip that last point there. So here's some random thoughts. Surveys like Planck, they lead to unexpected science. And I think in the case of Planck, lensing has really been a big surprise in the sense of how important it has been for CMB. And I think, as you put it very well, Martin, it seems to be opening a whole new field. This is something we did not foresee in the early days. Okay, we're almost at the end. Dust has also been very important and key to understand in terms of the CMB itself. So it's good to do as unbiased surveys as you can, and you will get unexpected results. I think we can say that the CMB has become a mature science. I mean, we have 3 generations of space experiments, and maybe there will be a 4th one. Lightbird has just been selected, and so we can hope that 10 years from now there will be a 4th generation. Of course, there's a lot of ground-based efforts. There's huge concordance. There's some glimmers of discord, and of course, the anomalies that people may prefer to look away from. I don't know. I don't know if one can say that the CMB has become an incremental science. I would not say that myself, but the potential for discoveries is uncertain, I think, at the moment. The thing I would like to say is that incremental science is good. It's how science progresses. We shouldn't be afraid of it, and we shouldn't be afraid to defend it when we plan experiments. Discoveries will come only if we do incremental science, actually. How do we go forward from here? I think Planck has shown us some of the limits, but there will be more, possibly. And for me personally, at least, I think at this stage we should diversify because we don't really know where the gold is. Will we find B modes? I don't know. We'll find out, I suppose. So my last slide. I think it's fair to say that Planck has been experimentally and scientifically a big success. It certainly exceeded all the requirements and expectations that we had at the beginning. It's not over. We're still generating some products, and you may expect something from the Planck collaboration as it tapers off into oblivion. CMB certainly mature and a precise science, but a lot remains to be done, discovery or incremental. And the Planck teams are still around before many of us retire. So I think if you want to have lessons learned, the best way to do it is to talk directly to the Planck teams. Thank you very much.
Thank you very much for the talk. As someone who's very much involved in Euclid, I was very interested to read all your comments. Once you get to a certain size of collaboration, one of the biggest problems is finding the correct information and finding also information which is up to date. And of course, Euclid is even larger than Planck. So what I want to know is, in Planck then, there was some person who was paid just to make sure that the documentation was up to date, and that everybody knew where to find the right document at all times, and the most up-to-date version of that document.
That was not the case. We didn't have a person that was paid to do that job, which is unfortunate. I think there should be. We had several different ways to deposit and distribute information, and they were all kind of organized in different ways. You're right. I think this is important. It has to be centrally organized.
It's wasting it. In fact, what happens now is, in fact, you have to know, instead of, if you don't know the answer, the thing you have to know is who to ask, who knows where the document is. Yeah. Because you're not going to know where the document is, yeah, as it organized currently, and that's right. A big, you see it very clearly when some new person comes into the collaboration, and how do they find the documentation? It's almost, it's very challenging.
Yeah, that's correct. And it comes to one of the points I kind of skipped over, which was about secondary science, if you like, or, yes, you know, yeah. There is a core of people who are well aware of what's going on. They don't need to be told necessarily, but there's a large cloud of people, and they are the difficult cloud to be made aware of things.
Other questions? Yeah, Martin.
So, Jan, you talked a little bit about data release, and you talked about documentation. What's your feeling about requiring or encouraging the release of the processing and analysis pipelines as public data products?
Yeah, I mean, I think at least in the case of Planck, it would be so difficult because the pipeline was so complicated and so on, that at least the official DPC pipelines, it would be difficult to release them in a way where you can ensure that people are using them as you would have used them. That is, document them, support them, and so on adequately. So we, I think, made a decision simply for lack of being able to do it, to not release pipelines. How important is it?
I may add, we strive very hard to be able to do this. And in the end, that depends not only on the code, that depends on everything, the library, the version of the library, the operating system, and everything. And just ensuring the ability of redoing internally was a huge effort. And so, well, now there are new solutions like Docker and so on, which may help, I mean, but that's in the future. At the time of Planck, there was just no way. Now, well, this was at some point, and that doesn't mean that we shouldn't strive for this, but we tried very, very hard, and in the end, you know, didn't do it. But some after-the-fact digested thing, and which we're in the way of doing, with M5 and so on, yes, I think that can be done. But all of the various iterations which went through, because we rebuilt all of those pipelines many times, there is just no way.
Yeah, I mean, Planck was very decentralized, if you like, in terms of pipeline building and running. if you have a you know, a system where you centralize things much more, you have a hope of being able to do that. But
well, I think what we've seen this morning is a great example of both the difficulties in running an experiment like Planck and the management challenges and how to deal with big groups that none of us were trained as when we went and got our PhDs, to a beautiful experiment and beautiful results. And so despite all the headaches, which I can appreciate having run big projects, it really has, I think, turned into a scientific success. And the legacy, as you said, will be the data that you provided to the community. So I think it's warm in here. We would all look forward to a half-hour coffee break, and we'll reconvene at 11 o'clock. Thank you.
oh. You mean the document in particular?
The document in
yeah,
particular,
yeah.
because people don't make it public.
Yeah, we think are important. They are not necessarily things
Okay, we're going to get going with Luca Pagano and measuring the optical depth to reionization with Planck.
Can you hear me?
Not very well.
Not so.
No, that's better.
It's better? Yeah. Okay. Where is the... So, good morning, everybody. First of all, I would like to thank the organizers, especially Francois and Sylvia, for the kind invitation. And today I will talk about something that was mentioned before, which is the measure of the optical depth to reionization with the Planck data. And the idea is to give you an idea also of the gigantic effort we had to make in the last years to clean from the residual systematics we had from the high-frequency instrument of the Planck satellites. I will also give you an hint of what we are doing in Ferrara after the Planck Legacy, trying to combine NFI and WMAP data at the end, and a few slides at the end of my talk. So why we want to measure the reionization optical depth, which is defined as the integral of the electron density along line of sight. And the reason is pretty simple. That's the relevant reionization quantity for CMB. And it impacts the CMB in mainly three ways. One is the damping of the temperature and polarization fluctuations inside the horizon. The second is the generates polarization signal on large angular scale. And the third effect is the kinetic Sunai-Zeldovich effect. And I will not talk about this. It's not the main topic of my talk will be the second effect, so the generation of polarization signal at large angular scale. So why we want to measure that? The reason it's pretty simple. Since the tau dumps the scales, it's completely degenerate with the amplitude scalar perturbations. So the only way of disentangling AS and tau is to measure polarization at large scale. And that's what we try to do with the Planck data. So what was the situation for Planck before the legacy analysis? In 2015, we could not use polarization at large angular scales because of those systematics. And we have to use the low-frequency instrument, which is much less sensitive, and where the level of systematics at that time were below the level we had instead in HFI. So the last years of our analysis in Planck was exactly to try to solve this remaining problem in the Planck data and try to improve the data at very large angular scales. So we already knew about the problems with the data, mainly due to temperature polarization leakage since 2013. And that was the reason why we didn't publish polarization in 2013. And so, but during the warming phase of HFI, so end of 2011, beginning of 2012, we measure the ADC nonlinearity of the detector. That was the main contaminant, the main effect that we had to consider in the data we didn't consider so far. And that's why we came out with a correction in 2015. We applied such correction to the TOI processing, and we could release polarization at small angular scales in the 2015 analysis. That was not enough for large-scale polarization. That's why we decided to go for a different approach for the legacy results. So we tried to solve such problem at the level of map making. So we wrote a new map making that was based on the striping, is based on the striping algorithm. But this map making is designed to solve for residual systematics and for the leakage due to ADC nonlinearity, plus other effects we had to consider. So the first thing is that instead of fitting one gain for the whole length of the mission, we start fitting more than one gain, so 128 for the cosmological channels, and that was following the apparent gain variation we had in our detectors due to ADC nonlinearity. That was correcting at least the linear part of the temperature polarization leakage due to calibration mismatch. The second effect, we removed a model of far side lobes convolving those far side lobes with a model of the dipole and the foreground. The third effect is we fit for bandpass mismatch, and you'll see later the level of improvement we had on the bandpass mismatch. And the third effect is we had to consider long time constant in our data that were not captured by the bolometric transfer function. And so we had that large-scale residual transfer function, and we fit them in our data at level of timelines. I could show many plots of the improvement we had between 2015 and 2018 at level of polarization. I decided to put this one, which is the survey difference null test, which means combining two surveys, other two surveys, and then make the difference between the two, trying to make a null test, so removing the signal in the difference. That's the situation we have in 2015. So in principle, you should see only noise here, but instead you see ugly structures, especially on the galactic plane, plus other large-scale structure everywhere in the maps in 2015. That's why at large scale we could not use such maps. That's the situation for 2018. Still there is a residual on the galactic plane. Probably the nonlinear part of the bandpass is still leaking in the difference. But for example, look at the 143 gigahertz null test, where we don't have CO and we don't have free. Basically, it's very negligible. Only dust is important here. The null test is very effective, and it's coming out very good. So, of course, in the null test, it's always dangerous to check data on nulls. One thing we try to do is to check all the pipeline through simulations. So what we did was to take a realistic dipole, CMB, foregrounds, realistic systematics, no photonic noise, only electronic noise in this case, and then we went through those timelines, through the map making, and then we remove after the map making the input dipole, the CMB, and the foreground. So in principle, we should see only a blue map here. Here I'm plotting polarization intensity for 100, 143 gigahertz. So in principle, we should see a blue map here. Where you see red, you have some residuals and you have systematics. That was the situation in 2015. So we applied the new algorithm, and that's the situation we have now. You see, still there are some residuals due to dipole leakage. Jean-Marc Delouis will discuss about that later in details. But those maps have a much lower level of systematics, and so we can try to use those maps for scientific exploitation, and this is what we did. So let's give a look also at the power spectrum, because at map level is always difficult to check numbers. Here you have auto spectra on the left and cross spectra on the right. The red line is the level of expected noise. Blue line is the quantity you want to measure in polarization. The blue lines are for the pre-2018 analysis. So you see the overwhelming level of residuals you have. And that's what we have now in the auto spectra for the 2018 analysis. Even better, of course, if you do cross spectrum, where still some residuals at very large scales are present, but below the signal we want to measure, which is the black line here. So we went for the analysis on data. So we first of all we have to remove the foreground contamination. So we have to remove synchrotron and dust. We use 30 gigahertz and 353 gigahertz maps as templates, and we made a simple template fitting, and we made the same kind of analysis on a set of 300 simulations. 300 simulations hand-to-hand, so with all the systematic effects, with all the problems we expect to have on our data. So we can look at the maps. That was the situation in 2015. Those are Q and U maps, left and right, 100, 143, top and bottom, Planck 2015, and that's the situation in 2018. Still, again, some residual, as we saw in the simulations. But we can try scientific exploitation of these, through those maps. So what we did was to try to cross-correlate 100 and 143 gigahertz to remove part of the contamination, of the residual contamination. Of course, since we did that, and since such residuals were not negligible with respect the noise, we could not go for pixel-based likelihood as we used in 2015, and as WMAP also used for the polarization analysis. So we had to find a different approach. And the other problem was that you see that this is the power spectrum in green, and blue is the average of the simulation. You see, for L equal to large residuals still present in our maps. I mean, well described by simulations, but still we have such contamination. So we could not go for an analytical approach, and we decided to go for a pure simulation-based likelihood. So what we did was to take our simulations, draw a set of simulated CMB sky, starting from theoretical CLs. We combine them, and we measure data probability at each multiple for each model we consider. So doing the empirical distribution, and then computing the probability of the data. We did that for many models, and then we interpolate for each multiple and model as function of the CL of the model itself, of course. And then the likelihood product is just the product or the sum. It depends if we think in probability or log of the probability of such interpolations. Ignoring correlations, we check that our QML provides basically uncorrelated bump powers. That's why we could go for this solution. Okay, what is the? There is one medium elephant in the room, which is the T spectrum is not included. Why is not included? But the reason is there are two reasons for that. One is that we have poor PTE null test when we consider TE. And the second reason is that the kind of likelihood we used is very complicated to generalize to other spectra, especially if we have to consider the correlation between different spectra. I mean, it's possible to do that, but the number of simulations we had, 300, was too low to allow us to do that. And you have to remember that every Planck simulation is very expensive from the computational point of view. So we collect all the functions I was describing before, and we tabulated them, and we built a likelihood model, and then we combined this likelihood module with the commander likelihood for temperature, as we did in 2015 and 2013. And that's the value of tau we have measured. So this is 0.051 plus or minus 0.09. This one has to be compared with the value we published in the intermediate paper in 2016, that was 55 plus or minus 9, and we have a 0.5 sigma downward shift compared with that value. The reason of that is there are several reasons that are causing that. One is the fact that we decide to be more conservative in our data in 2018, so we discarded 1,000 rings at the end of the mission. The second reason is that we improved the synchrotron correction that was not included in 2016. And the third reason is that the new simulation pipeline have been completely rewritten in 2018, and the control of the simulation is much better in the new analysis. There are several limitations of our approach, and then you'll see the paper coming out in few weeks, and so you can read about that. I will list here. I'm listing here the main ones. One is that, of course, we depend completely on simulations. This is a limitation of our approach, and of course, lower and lower is the level of systematics, less is the danger of doing that. Of course, we check that our simulations are good to do such analysis, but of course you cannot be 100% sure about that in any case. The other thing is that that there is a clear coupling with the foreground model, and so it's related to simulations that the foreground model we used has an impact in our analysis, and that's we try changing the foreground model. We don't see any change in the results, but that cannot be. We cannot be sure 100% because at the end this is just a model. And the third aspect and third and fourth aspects are connected. We have very large scatter for the first two modes, L equal 2, L equal 3, and so our measure is completely dominated by L equal 4 and L equal 5. You'll see later the presentation by Jean-Marc discussing this point in more details. So we made several consistency tests. I put a few of them here. We changed the mask and we see the stability in our results. We change also the pipeline for producing masks and we don't see any major difference. We remove multiple each time since we have a likelihood L by L, and we see the deviations, but we check them versus simulations, and this is completely inconsistent with that. We also took all the data set available we had between WMAP and also LFI and tried to make all the cross spectra and try to measure tau for each of them. And again, everything is pretty consistent. So we are consistent with all the tests we did, and we did many tests, not only validation of the likelihood, but also stress tests, changing masks and inputs in the data. We also did for data split, I'm not showing that here, but we also make estimation from data splits, and everything is consistent with what we have in the full mission data. So let me go through other two topics that are complementary with what I presented. One is the legacy LFI analysis, which will not be the baseline, and it was not the baseline, but still it's interesting to see what we did for LFI. The analysis was basically the same we did in 2015. The only difference is that we have a new version of the maps, of course, and we could put back survey 2 and survey 4 in this analysis, and what that we had to exclude in 2015. Again, we cleaned with 30 and 353 as in 2015, and we made a pixel-based likelihood. So it's even the approach for the likelihood is different in this case. We redo all the selection of the mask, and we added more tests with respect to what we did in 2015. Also in this case, for LFI, we did the sky fraction test. So we changed the sky fraction used for the tau estimation, and we checked that the value of tau is stable, or at least the fluctuation we see are compatible with the simulations of signal and noise, of course. Of course, considering the common sky between each sky fraction. Also, the PTEs are pretty good, slightly better than what we have in 2015. And we also compared the results with WMAP computed on the same sky fraction. And we made a null test, making the difference and measuring tau, and we don't see any signal. And then we compute tau from WMAP, which is very consistent with LFI. The final value for LFI for the tau constraints, including TE in this case, because we're using a pixel-based likelihood, it's 0.063 plus or minus 0.020. So a factor 2 worse than what we have with HFI. That's expected, but still perfectly compatible. Let me spend the last few minutes about a different thing we did instead. We are doing after the legacy analysis. That was another piece of information that we can add to the global picture of measuring tau using large-scale polarization CMB data. And this is involving LFI plus WMAP. So we try to do what? We try to combine the two data sets where we have a good description of the noise. That was not possible with HFI, but for LFI and WMAP, we have covariance matrices, and we trust them. And so we try to make a real space estimator, so a map-based likelihood instead of a power spectrum-based likelihood, as we use instead in HFI. Why we want to do that? Because maybe there are studies that are not accessible through power spectrum, but we want to have something that acts on maps. Of course, we have a potentiality of 20% tau estimate. It's not at the same level of HFI as error bar, but still it's interesting to look at that. Okay, a quick review of the method. The method is the same we use for LFI. We consider Ka, Q, and V bands of WMAP plus the 70 gigahertz. We made the template fitting real space as we did for LFI, and then we combined them up inverse noise weighting. And then we built a pixel-based likelihood. That's the mask selection. We made the mask selection based on chi-square, and we found actually better chi-square for LFI from what we did for the Planck Legacy, because in this case we completely redid also the mask pipeline, also for WMAP, because the WMAP mask were tuned for a different data set, which has no smoothing. Instead, since we are smoothing the WMAP data set as we have and we did for LFI and HFI, the WMAP mask processing mask were not good enough for our analysis. That's the power spectrum for different sky fraction with error bars. This is QML power spectrum. And that's the PTE for the baseline analysis, which uses 54% of the sky. That's the plot comparing different tau posteriors for different sky fractions from 30 to 55, 30 to 50, and 35 to 59% for LFI WMAP and LFI plus WMAP. Everything is pretty consistent. We check also on simulations again if the scatter we see is compatible with simulations, and the PTEs are always better than 10%. And that's the final value we can find combining LFI and WMAP data, which is 0.068 plus or minus 11, 12. Again, this includes TE in this analysis. So let me conclude with a couple of plots. Okay, perfect. One is the posterior side presented here. Here in this case, I decided to go only for the low EB likelihood version for WMAP, LFI plus WMAP and LFI. Try to compare apples with apples. Here, all those three tau estimates are coming from EE only, basically, combined with the TT likelihood commander. Those are the values we have, are pretty consistent with HFI still low. There will be an update made by Jean-Marc later on this value using a refined version of the HFI data, which is very consistent also with those values here. And this last plot I want to show is the global picture what we have on tau coming from CMB at large scale in polarization. Not only because here I put also TT plus lens plus bow constraints, so not using polarization at all. And those are all the plots. So what Jean-Marc will show the red line. I presented the green here and the yellow and the blue here. The only value is not, of course, clearly consistent with what we had is the WMAP one. Here I simply rerun the WMAP likelihood as it is, fixing the IL parameters. And, but of course, we already saw that taking the WMAP data and reanalyzing them, cleaning the dust, not with their dust model, but cleaning it with the 353 gigahertz, so using actual data, shifts the tau value also for WMAP in the same region of the power spectrum, which is between 0.05 and 0.07. That's it. Okay? Perfect.
Time for questions. Yes.
Results on tau are already exquisite from Planck, and I would say that in 2016, Planck was the first experiment to combine the three probes of tau that you were mentioning: the temperature, the polarization, and the KZ. And this is unique from now on by Planck.
Sorry,
There's
I
another
didn't
hand.
mention that.
So you said that there might be still some systematics, but you worked on it and it seems like it's under control. So say these systematics were there still. Which way would it move the other cosmological parameters? Would it make it closer to the ones that are in tension? Or
I mean, given the value we have, I don't think there will be a major change in the other cosmological parameters. There will be a shift on the ES. That's because the degeneracy is pretty tight. But if you think about the infamous lens parameter, I don't see any. Karim also is confirming that, but I don't see any shift in a lens or in the significance of the value of a lens we have, even moving, for example, the red line, going back slightly higher, like we measure, like Jean-Marc will present later. We don't see any change in the other cosmological parameters. Even for, I don't know, some of the neutrino masses, for example, which is something that you want to measure, knowing better the tau, you don't see any clear improvement, any significant shift.
Did you have your hand, Sylvia? Yep.
Can I add just to your answer? I mean, it's to solve some of the weird things in Planck. I think you would need a tau which is 0.13. I mean, something really out of this plot. I mean, for a lens at least. I mean, something really high. If you change a little bit tau, it can have an impact. For example, for the sigma 8. Problem. Yeah, right. With the new value that we had this year, I mean, from 2016, I mean, we actually made the tension on sigma 8 a little bit less significant, like by half a sigma, because you decrease tau, you decrease AS, and so you decrease a little bit sigma 8. But we're talking about, changes which are, less than a sigma. So yes, here and there you can, have small changes, but as Lucas said, it's not solving radically things.
If there are no further questions, let's thank our speaker again.
Thanks.
And we now have Anthony Lewis open questions after Planck. Would you like a 10 or a 5-minute?
I think 5 will do, thanks.
Right, so I thought I'd take a bit of a step back. So I've been given this incredibly broad topic to talk about. I'll just talk about some of the basics about what Planck's actually measuring and how that relates to other observations, and something about the tensions and what we might be able to tell in future with future observations. So just to remind you, the CMB we're mainly measuring in Planck is cosmic variance dominated in the temperature. So we're seeing these fluctuations from inflation, but we don't see them at the end of inflation. We see them at recombination. So what we see is these fluctuations from inflation evolved forwards in time by this physics we think we understand about the early universe. It's just basic gravity and diffusion and sound waves propagating. And then what we see is last scattering surface at the time of recombination, when it has this very characteristic scale imprinted on it, which is the sound horizon, which tells you how far a wave can propagate by the time of recombination. And there are a very large number of peaks measured extremely accurately by Planck. So we get a very accurate measurement of RS here, which is the characteristic size of these perturbations, the largest scale that's had time to collapse by recombination. So then Planck, what we do is we measure angles on the sky. So if the hot Big Bang is over here, there's some period of expansion to get to recombination at redshift 1000 or so. We're at redshift 0. We look out at the sky. We measure an angle on the sky corresponding to the scale of the acoustic peaks in the temperature spectrum. And the sound horizon here tells you how far something can have traveled in the time available by recombination. And this is that angle that's measured incredibly accurately by Planck, just because you've got so many acoustic peaks over the whole sky. And this is now 0.03% precision. It's almost the most accurate measurement in cosmology, almost as accurate as the background CMB temperature measurement. So this is really, as far as other data is concerned, this is basically just a delta function, which is an incredibly accurate measurement. So once you know theta star, then you can worry about how the other parameters affect what you're seeing. So this is all very well known. Just to remind you that if you fix the matter density in theta star and you change the baryon density, what happens is the even and odd peaks in the spectrum go up and down by different amounts. So you get this rather characteristic signal here with even and odd variation. And then you can use that and you measure the baryon density. And that agrees quite well with element abundances, as we heard earlier. If you know the baryon density and you fix theta star and you vary the matter density, then the main thing you'll change is the relative height of the peaks. Because we've got lots of measurements all out here. This is a bit less robust than the baryon measurement, but it's still pretty robust. We've got lots of different peaks. You don't have total freedom in the foreground model. And this gives you, again, a very nice measurement of the physical matter density, omega m h squared. Okay, so if we now assume things about the physics, we can actually calculate what this sound horizon should be. So we're going to assume that there's photons, so there's 3 standard neutrinos. It's lambda CDM. We know the temperature of the CMB, so that tells us how many photons there are at that redshift. And we've measured the matter density and the baryon density. Then you can just work out what you think the sound horizon should be. So you just integrate the co-moving sound speed between 0 and recombination, and that gives you this number, about 144 megaparsecs. Now we've measured this angle here very, very accurately, and we can predict what this should be. So we can infer what this length must be, chi star. So from that we can infer that the radial distance must be about 14 co-moving gigaparsecs. You can also calculate what the co-moving distance should be. So you write down your integral here to get the co-moving distance, and you expand it in lambda CDM. So that depends on the matter density and the cosmological constant. But if it's flat, we assume it's flat, then you can relate the cosmological constant, so the matter density, and then the only unknown in this parameter is h0. So that indirectly is how Planck gets this h0 measurement of 67 plus or minus 0.6 or so. So there are a lot of assumptions going in here, both about the early universe physics here, about the sound propagation, and about this late time geometry and the fact that it's flat and the matter components in the late time. There are systematics and things in Planck at a very low level, so it's quite easy to shift this thing around by half a sigma, maybe 1 sigma by messing around with what you do. But the point is this error bar is incredibly small, so just shifting it by half a sigma or 1 sigma really doesn't shift the overall value of 67, 68 very much. You can't shift it up to 72. It seems very implausible that a simple systematic could do that. So can you check it from other things? Well, you can, because you can also measure this sound horizon in the baryon oscillations. So the sound horizon in the photons is measured by Planck. The sound horizon in the baryons is measured by the baryon acoustic oscillations at low redshift. So a redshift of 0.5 or so. You see this same acoustic scale that you can calculate here, both transverse to the line of sight, giving you a BAO angle, or along the line of sight, giving you a change in redshift between the two ends of the sound horizon. And the change of redshift you can just relate to a change in distance by dz by d chi, and dz by d chi is h. So that tells you h if you know the sound horizon. And then if you make this plot, assuming lambda CDM of the evolution of h, so this is the co-moving Hubble parameter here. So this is the Planck prediction with the co-moving Hubble Hubble parameter decreasing, then it accelerates here when lambda domination kicks in, it goes up again, and we get around 67, a redshift 0. It's extremely consistent with what you see in the BAO, assuming the Planck sound horizon and assuming lambda CDM. You get these measurements here, all agree really quite well now with the Planck prediction. And then, of course, there's this anomalous point, very low redshift, which is the direct measurement of H0. So this has far fewer assumptions about cosmology, almost no assumptions about cosmology in it, but of course it's a completely different measurement and it is only one completely independent thing at the moment. Strong lensing is beginning to be interesting as well, but they've got bigger error bars at the moment, but they're also getting numbers a little bit up here. So at the moment this is about 4.4 sigma. So I just want to emphasize that this is really a precision measurement in Planck. It's really quite hard to see by eye these kind of differences in the Hubble parameter. So this compares a best fit with a Hubble parameter of 67 to a best fit with Hubble parameter of 73. Of course, if you do that, you will change other parameters as well because they are degenerate with each other. And you can see by eye in the temperature spectrum here and the TE spectrum, they both look like perfectly good fits to the data. If you look at the differences, well, this is the difference to the lambda CDM is black, and red is the difference to H0 of 73. If you force it to be 73, and now you can see there are oscillatory differences, and maybe it looks a little bit of a worse fit up here, and maybe it looks a bit worse fit over here. It actually looks a better fit here. But this is really very difficult to see by eye. Yet, if you look at the actual chi-squareds, this is a very large difference of about 82 in chi-squared. So we're really getting to precision cosmology. It's precision measurement. We're getting things by accurate measurements, things that are quite hard to see by eye. We do, however, have some cross-checks on them. So we've heard about CMB lensing. So CMB lensing basically measures a slice through three-dimensional parameter space, or a line through three-dimensional parameter space, in only the matter density, sigma 8, the fluctuation amplitude, and the Hubble parameter, giving you these dots here. And then if you combine with BAO, which gives you a different slice through that space, you actually get a very narrow intersection. And that intersection point here gives you a Hubble parameter of about 68 plus or minus 1. And if you add a theta star constraint, which is very robust in lambda CDM from Planck, then you again get to a 68 plus or minus 0.7. So there's good consistency within Planck with this rather low number in lambda CDM. And you can also just throw away Planck and get a very similar number by different means. So instead of getting the baryon density from the Planck measurements of the acoustic peaks, you can instead get it from the element abundance observations. That will tell you what omega BH squared is. You can also use the supernovae observations to measure omega M. If you assume lambda CM, then you know all the ingredients, and you can just make exactly the same argument as you made from Planck with these different inputs. So this green contour here shows what you get by combining BAO and Pantheon to measure the matter density and element abundances to measure omega BH squared. And again, you find a relatively low value of H0. It extends up here to slightly higher values. But if you add a better measurement of the matter density, for example, from CMB lensing, you get down to this gray contour, or you add a measurement of the angle on the CMB, and you get down to right down to here. So these contours here are basically independent of the CMB measurement. So you've got two independent measurements that are both giving you low values of H0, and it's pretty hard to get values up here. This degeneracy might fluctuate up that way, but of course the CMB would have to fluctuate up that way, which gives you completely different values of omega M. So this is the key open question, I think, at the moment, and it is very interesting. Why is this H0 local measurement, and possibly from strong lensing, in such strong tension, assuming lambda CDM? So it could just be a fluctuation, but 4.4 sigma is getting pretty unlikely. People have been saying for a while, you know, this would be interesting if we had a few more sigma. You've got 4.4 now. I mean, how many do you want before you start taking this seriously? So there could, of course, be something wrong with the local measurements or the error model. So we're going to hear much later in the week a lot more about local H0 measurements. I'm not going to talk about that. Could both Planck and BAO be wrong? This is beginning to sound pretty implausible, I think. So I think that's probably the least likely explanation. Could lambda CDM be wrong? So of course that's the most interesting one, and Planck were all desperate to find something that's not lambda CDM because it's getting very boring after all these years of finding lambda CDM. So what are the solutions? How can you change things to make things work? Well, I think the simplest one is probably to have some new physics before recombination. If you just make the universe expand a bit faster, you can make it reach recombination a bit sooner, you can decrease the sound horizon, and that will translate into a larger H0. Because that sound horizon entered the BAO and Planck, then you can shift both the BAO and the Planck measurements simultaneously to higher values. So you can consistently change both numbers up to give you a high value of H0 by doing that. You could try and change the angular diameter distance at low redshift by playing with dark energy or something's going on there. This is pretty tricky, I think. So you put in a physical model with equation of state bigger than -1, actually that goes the wrong way. It's very easy to make H0 even lower from Planck. It's quite hard to make it go higher. And of course, you also have to fit the BAO and the measurement of the time dependence of H from the supernovae. So this is a very constrained problem, and I don't think anyone has yet come up with a very plausible way of doing it from late-time physics, but it's certainly a logical possibility. There could be some new physics or unusual conditions in our very local neighborhood which is messing up the apparent local H0 measurement from the global one. So that's, I imagine you can measure there some rather obscure anthropic reason maybe that the local physics is a bit different that we haven't thought of yet. So that's a possibility, but again, maybe not so likely. Or of course it could be some super contrived combination of the above, and if it is, I think I'm going to give up physics. So what could the new physics be? So the simplest thing, as we heard, is adding something like extra neutrinos or something. If you had more relativistic degrees of freedom, the universe expands faster, you get recombination sooner, smaller sound horizon. So this is ineffective, just adding extra degrees of freedom. And the trouble with doing this kind of thing is that Planck really doesn't like adding extra degrees of freedom. So you do change the acoustic scale, but of course you also change the damping tail of the CMB. So the detailed structure of all those higher peaks changes in significant ways that you've actually measured very well with Planck. So if you add this parameter, Planck actually still doesn't shift at all, really. It still prefers around 67. You make the error bars a bit bigger. If you do a joint constraint, you can pull things up a bit, but it's still nowhere near up here. So it looks like a very unnatural solution. It still has to be a very large statistical fluctuation. And this seems to be true for basically all very simple extensions that you could think of. Of course, you can think of more complicated extensions. So, for example, you can add interactions or new species that interact or new interactions between things that are already there, we think are there. So one thing to note here is that the relationship between theta and the actual position of the peaks on the sky does depend on the cosmological model. So what you're measuring is the position of the acoustic peaks very, very accurately. Interpreting that in terms of the sound horizon depends on things like the phase of the acoustic peaks. So if you change the phase of the peaks by changing the interactions of the neutrinos, for example, you can shift the sound horizon whilst keeping the peaks in the same position. So you have to be a little bit careful about thinking about theta star, which is extremely robust in many models, but when you start playing with interactions, it might change. Another one people have been playing with is having early dark energy. So this seems a bit unnatural because you have to put in about 8% of the matter density around matter radiation equality, and then it has to fall away really, really quickly in order to get the CMB in the temperature from Planck matching reasonably well. But this is probably the best fit people have come up with so far. It's a long way from being natural or very physically motivated at the moment, but it's certainly interesting. So, of course, this is the really big new question. What's the actual model, if that's the answer? So what we do know is that the Planck temperature measurement is nearly cosmic variance, and whatever you do, it's going to have to look an awful lot like lambda CDM in this Planck CMB temperature spectrum. So that's been measured very well. It also has to fit TE and EE, the polarization spectra, quite well, but of course Planck has got a lot of noise on those still. So going out to small scales, there will be a lot more information in the future. So it's possible that you can just about manage to fit TT whilst leaving TE okay for Planck, but in the future it will be completely ruled out. So to fit TT, typically what would happen if you add a new parameter, or add several new parameters, you add some new physics in the early universe, you will change the damping, you will change all sorts of details of the acoustic peaks, but you've got this freedom to fudge things around by changing the baryon density, the matter density, AS, NS, and so on. So maybe you can just about fudge things up to get things to work and look miraculously like lambda CDM in the temperature spectrum. But if you do that, one thing to note is there is new physics. That does, as a corollary, mean basically that the measurements of parameters in lambda CDM are probably wrong because you've compensated them with some physics that we aren't modeling. So for example, if you're interested in inflation, the measurement of NS, assuming lambda CDM, could be significantly wrong. Let's measure that. Remember that plot earlier where H0 was 73, NS was actually about 1. So that's a very different physical model of the early universe. So this has very strong, important implications also for other parts of physics as well as the pre-Roy combination physics itself. And also, it's almost impossible then to actually get the polarization to look like lambda CDM as well. And that is actually incredibly good news because that means you can go and look for it in the future. And you should see a very distinctive signal in the polarization because of you can measure up to 4,000 potentially. L equals 4,000 in polarization at very high signal to noise. So as an example of that, Simon's Observatory will be measuring from the ground much higher sensitivity and resolution than Planck. And it will be making a very nice measurement of lots and lots of peaks in the polarization power spectrum. So if you take, for example, this early dark energy model of Poulin et al., which has about 8% or so dark energy around matter radiation equality, currently, if you combine H0, Planck, and BAO, you get a big ellipse that goes out like this. It's pulled a little bit away towards higher dark energy fractions along the bottom here. But if you take the best fit here as a fiducial model and say, what would Simon's Observatory see, then you can forecast something that looks like this blue contour here. So even if H0 is 71, this gives you such a distinctive signature in the polarization on small scales, the Simon's Observatory should start to see this at about 5 sigma. And I think this is a pretty generic statement. It's going to be extremely hard to find any way of changing pre-recombination physics that doesn't give you at least 5 sigma in polarization data that will be available soon. So if this is right, the new future, the new coming up CMB polarization measurements should be super exciting. Are there any other hints of new physics elsewhere? So there have been these claims about low sigma 8 compared to lambda CDM from Planck. And this is a much more murky question, I think. So this is the DES constraint joint analysis here, which gives you some contour. It looks a bit lower than Planck, but this isn't really discrepant to any significant amount. It's a little bit in tension, but the contours overlap, so it looks fine. If you go to smaller scales and start modeling halo occupations and things, you can end up with contours that look really quite discrepant. But this is a very long way from being simple, clear, robust, linear physics that the other measurements are based on. So the authors of these papers are not claiming at the moment that these are robust detections of violations of lambda CDM. There's a lot more work to do to understand the astrophysics. Weak lensing is perhaps a bit more interesting, because here you can cut to scales where things are still quasi-linear. Basically, the physics is sort of understood, but of course there are effects of nonlinear effects in there still. So this is the situation as of last week on lensing comparison. So DES lensing here is in green, giving you an ellipse there. Hypersupreme cam lensing, this is the second analysis using the correlation functions that came out about last week. Gives you that grey contour, which is very consistent with DES. There's Planck CMB lensing, which gives you a slightly rotated contour because the source plane is a much higher redshift and actually extends rather less far in that direction. They overlap very, very well. And they also overlap very well with the Planck power spectrum measurement, which is this small green thing here. So at the moment, they all look extremely consistent in lambda CDM with the Planck measurement. The kids' contours down here do actually look a little bit in tension, but only at the 2 and something level, so not massively discrepant. I should say you have to be a little bit careful about comparing these kind of figures because, of course, there's a lot more parameters than 2 parameters plotted here. So, for example, this shows the matter density against log AS, the primordial fluctuation amplitude, colored by H0. And you can see that this HSE contour actually spans a massive range of completely implausible values of AS and very wide range of H0 values as well. But miraculously, if you actually look at the region of parameter space here, 0.3, 0.8, corresponding to Planck, actually you do get values of AS and H0, which both agree with Planck as well. So this is actually looking like quite an interesting non-trivial consistency check at low redshift. The things are looking more or less okay in most of these measurements. And then, of course, things had to be not that simple, and as Martin was saying, things are in flux. So to demonstrate that, there was this paper this morning, just to throw me off. So here, I think the kids have taken the DES data, and they've done a recalibration using spectroscopy of some of the DES redshifts in their lensing analysis. And what they claim is that the contours from DES actually shift down and start to agree much better, strangely enough, with the kids' contours, giving you a joint constraint that's down here. And now the two sigma contours of Planck and this joint lensing constraint don't intersect. But I think Martin's point is the right thing here. This is in flux at the moment, so we really don't know. And there's nothing convincing in CMB lensing, in galaxy lensing or CMB lensing to indicate a violation of lambda CDM. But of course, this will get better, hopefully, if the number of nuisance and parameters doesn't increase too fast. So this will potentially be a very interesting extra way of confirming or ruling out some models of new physics in the early universe. There's redshift distortions. Currently, there's nothing very interesting here. You just plot the Planck prediction, and everything has pretty wide scatter, and it all looks very consistent. So I think the summary is at the moment there's no compelling evidence of deviations for lambda CDM in large-scale structure, but there could be, and it's certainly worth looking for, and it will get hopefully clearer in the future whether there is. And if you can tie some story about the early universe expansion to the growth of structure and the growth rate and sigma 8 and things and tie them together with low redshift, then it could become a very compelling story about new physics. What about these rather weird things in Planck data itself that we don't really fully understand? So there are a bunch of things which are not really obviously anomalous, but not obviously super consistent either. So they're sort of 2 or 3 sigma level. Could these be hints of new physics? So that certainly, they could be. As far as we can tell from Planck alone, if we only had Planck, I think we'd say these were statistical fluctuations. There's nothing obviously anomalous about them. But combined with other data, maybe they could be seen in retrospect as hints of new physics. So just to remind you about what these are, there's this funny dip, TELF 27 here. It's very hard to quantify that in a sensible, meaningful way, given that it's a posteriori. But this is not super significant, but maybe 2 or 3 sigma, depending on how you quantify it, maybe up to 4 sigma. So it's certainly visually striking that it's there, and it does affect other parameters as well. There's this a lens anomaly, so I'm not going to talk about this in detail because there's a whole talk about a lens coming up shortly. This is basically the peaks look a little bit smoother than they should be from the predictions in lambda CDM from the Planck model. And if you try and fit more smoothing, you see more smoothing preference at around 2 to 3 sigma, depending on what you do. However, this appears to be nothing to do with actual lensing. This is something to do with the smoothing of the TT acoustic peaks. For example, the lensing reconstruction amplitude is perfectly consistent with lambda CDM, as we showed before. But there could be some hint of other new physics if it could somehow affect the peaks of the spectrum in this interesting way, or shift parameters so that the predicted peaks then look better. There's also this possible tension between parameters from low L and high L, so people were surprised perhaps at the shift in H0 between WMAP and Planck. So that's the difference between about L of less than 800 and bigger than 800 in the temperature spectrum. And you can see here in the bottom triangle here, for example, the blue and the red contours show the constraints from those 2 different regions, and they only just barely overlap in many of these different parameters. This does not appear to be anything more than a very fairly modest statistical fluctuation. So, for example, if you use EE in a baryon prior, you get these green contours, and they happen to lie exactly on the intersection, which is what you'd expect if it was a statistical fluctuation. If you add polarization, then you get the contours in the upper right triangle here, And then there is still a little bit of difference between them. Again, it looks quite consistent now with a statistical fluctuation. So I think from Planck alone, there's no reason to think this isn't just a fluctuation. But of course, if there was some new physics, in retrospect, this might seem like a hint that it's there. So I think that's actually about all I want to say about this. So I think this is the big question at the moment. Why is this discrepancy nearing 5 sigma? Will it get better? Can we get an independent measurement of H0 from local measurements? Then it starts to become really convincing. Is lambda CDM correct, or is it at least observationally indistinguishable from correct or not? If it's not, it seems the simplest solution is probably to change something before recombination to shift the sound horizon. And if that's true, and H0 is high, then you should see that very, very clearly with coming CMB observations. So the future is going to be very interesting. But it also means that some of the other measurements of Planck parameters, assuming lambda CDM, will be significantly wrong. So we then have to start examining other parts of what we think we understand about cosmology as well. I have to say that none of the models people have currently attempted look terribly compelling or natural. They tend to have a lot of free parameters. They don't improve the fit very much. So at the moment, I think there's no compelling model for doing this. If you can come up with one, that would be very interesting, especially if it can fit some of those other curiosities simultaneously, and maybe also fit low redshift data better as well. It could be like late-time physics. This is looking contrived, I think, but again, you know, if you can come up with some model that looks convincing, you can test with other data, that would be very interesting. And then if lambda CDM is actually right after all, then of course we have to find out what's wrong with that local measurement. Or could it really be that Planck and BA are both simultaneously wrong? And if it is, then of course we're left back where we started from, and we know that lambda CDM tells us everything about the universe, basically, except that we don't know what the lambda is and the CDM is. So those questions remain. Thanks.
Thank you for leaving open questions in Lambda and CDM. Questions?
Thanks. So, okay, that's supposed, I mean, there may be models with new physics, I don't know, dark energy, modified gravity, interactions, as you said, also that might decrease this 5 sigma, maybe not the whole 5, maybe, I don't know, down to 2 sigma, and then maybe it would be enough. But the question is, yeah, you say that there's no model that would be convincing enough. So when do you think a model would be convincing enough? Let's say, when would the model be convincing enough for you? Would it be, would you need a model with like the same number of parameters as lambda CDM, or would you put a limit to the number of extra parameters? Or when do you feel that a model is convincing enough? Because again, should it resolve the whole 5 sigma? Should it resolve down to 2 sigma? Or well, otherwise, it's difficult to understand what's how to convince you.
Well, you could come up with something that looks physically compelling from purely theoretical things. I think that's probably unlikely at this point. At the moment, otherwise, I think nothing that's been designed to fit this tension is going to be compelling because it's been designed to fit this tension. Mm-hmm. If you then measure CMB polarization on small scales and that fits that model, that's going to become very compelling.
But models of modified gravity or coupled dark energy were there long before this tension existed. So I don't understand this. There are models of coupled dark energy or modified gravity, basically all models which have an extra interaction that were there and were thought long before this 5 sigma tension was in place. So in this sense, they were not fit for that. Maybe the last paper that you cited of 2019, maybe yes, but this using, again, interactions, this is a base, it's even maybe the first thing that you do when you think about modified gravity, inserting a new interaction. So in this sense, I don't think that this idea of like creating a new interaction was done to fit the 5 sigma H0 was there when people started to think about dark energy and modified gravity in first place.
I think that's true, but I think it's also true that none of those models people wrote down before this actually explain this.
Well, actually, I mean, okay, that was published in 2000, yeah, maybe 7, when the tension was at 2 sigma or 3 sigma. So, But of course, it's obvious that you try. When the tension is only a tension, and then people write about that, then you doubt that you should write a paper to explain a 2 sigma tension. Then when the tension becomes a 5 sigma, then you think that the model fits the 5, is done to fit the 5 sigma. I mean,
I think we all agree more data are needed and higher accuracy. Any other questions or comments? Yeah.
Maybe, Anthony, you said that it's unlikely that the DAO and Planck measurements are both wrong in determining H0 because they are not completely independent, but nevertheless rather independent. And what about the strong lensing and the supernovae? They are quite independent. Why do they both get this high value? Are they both simultaneously
on their own don't get high H0. I mean,
sorry?
You can't get high H0 from supernovae alone. You have to have some distance anchor somewhere.
Sure, but I'm now of course talking about the supernovae F8, the reset-all type measurement compared to the strong lensing measurement.
Yeah, well, I think at the moment the strong lensing measurements are sufficiently large that some Planck's fluctuating up by 1 sigma would be consistent with those fluctuating down by 1.5 sigma or something. I can't remember what the numbers are exactly at the moment.
That's fair.
What do early dark energy models do to sigma 8?
I think it doesn't change sigma 8 very much. It depends, of course, on what you put in. I mean, there are at least 3 different models of this. In terms of the actual H0 discrepancies, they all do quite similar things. But in terms of what the sound speed is and how they decay away and things, you can change what sigma 8 does. So there are other people here better qualified to answer that question. I think you can shift it a bit, but it's quite hard to shift it by a lot, but I could be wrong about that. I haven't looked at it.
Okay.
Right. So one of the things in the H0 inference is that we don't really have data between the last high redshift supernova and the CMB. So between redshift 1.7 and 1100. Do you think there's a specific data set or a model that modifies standard expansion history in that range that could be the explanation, or is there something specific that we should get at maybe redshift 5 or 6 in order to try and see if there's something there?
It's just very difficult because if then you have physical dark energy models, that goes the wrong way. You can make H0 lower very easily, but it's very hard to make it go higher by doing that. So it's certainly not impossible, but I don't think anyone's got any very plausible way of doing it.
Contrived, yeah.
Just a quick remark, you mentioned the low L, high L, say fluctuation. There's another aspect to this, that the FNL is at the 2.5 to 3 sigma. At low L, just the range of L's that are covered by WMAP. Let's say between 2.5 to 3 sigma after the fluctuation of non-Gaussianity, which then goes away when you add 10 times more orders. So, maybe there's also a false symmetry in saying L from 0 to 400 and then, or 0 to 800 and 800 to 1600. That sounds like you're cutting in the middle, but actually you're cutting at 1 to 10 in terms of number of modes.
Right, yeah.
I have a question. What kind of new physics in local can lead to relax the tension?
I have no idea. Sorry.
Okay, let's thank our speaker and move on. We'll now hear from Jean-Marc Delouis on improved map-making approach.
Where is my talk? Il est où mon truc? Merci. Comment ça affiche? Je l'ai comment? Je sais pas où c'est. C'est exprès pour le suspense.
J'espère que ça va marcher. Ouais, j'ai failli le mettre. Super. Ok. Et le passage. Ok, super. Okay. So thank you for the organization to give me the opportunity to talk about a new data set that is done through on behalf of the Beware on the Deep Sea group. I just want to remind you a little bit of, oh, yeah, it works. Yes. About the way the Planck does map. So here you have a, oh, it stopped. Okay. Okay, it's cool. Okay, I will do it without the video. So the concept is Planck has a rotation, 1 rotation per minute, and it scans the sky every minute. Every hour it turns a little bit, and at the end, after 6 months, you have 1 survey, so 1 full map. And for HA5, we have 5 of it. So this is the most important thing, in fact, of Thrall, is the fact that if you cross 2 scans, and if you believe that CMB doesn't change between the 2 scans, which is, I think is true, the only difference between this measure between these 2 scans is should be modeled by all instrumental systematic effect. That's what we did with Thrall. So the idea is to use all this information to improve the model of all systematic effect and to improve the map at the end. Little bit of history. At the beginning, I try the pointer, this one is okay. So at the beginning of the timeline, the processing was divided in several tasks, in 4 tasks. You had the map making for 2013 and 2015, which was an independent task. And the calibration was, for instance, done independently. With the Planck Legacy 2018, Thrall 1, which means steamroll, sorry, I forgot to tell it, was used and integrate the calibration and part of the component separation. This is for foreground and the color correction. On Thrall 2, you had some information from the timeline pre-processing and you improve the component separation. The goal at the end is to have everything together. The idea driving all this effort is the fact that if you do things simultaneously, you decrease the impact of the degeneracy if you are working in an incremental way. Here is a little bit of the story again. This is the Planck collaboration release. So we have the 3 releases that you may know. The Thrall 1 integrates in the map making the calibration, the color correction, the effect, it has already been said by Luca. Transfer function, ADC, I will go a little bit deeper on this ADC part. And today, I talk to you about the 2019 maps, which is Thrall 2 effort. It had some improvement on the detector polarization parameter, improve a little bit of correction and transfer function, and mainly the biggest effect is the story of analog to digital converter nonlinearity that is clean. So what is the ADC nonlinearity? ADC-NL for the short name. On board, to convert the detector to digital numbers, you have an ADC converter for each detector. And unfortunately, the space-qualified ADC has nonlinearity, and their nonlinearity is different for each detector. So we made some effort to pre-process this in the timeline level, and Thrall 1 managed this as a time variation, gain time variation, which is a first step of cleaning this. So let's go back on the simulation. I put this small picture. When it's simulation, you have this. And when it's not there, it's data. So to check what happened on simulation, that's a plot already shown by Luca. So it's 100, 143. This is a polar intensity. And what you see here is well reproduced by ADC nonlinearity, and that's what you see in the data. So if you add some gain variation, you are going to this. If you are going to clean the ADC more properly, you're getting something like that. So I just blink. So you see that the empirical cleaning, which is done in Thrall 2, which using what we understood of the physics of the problem, is very efficient to remove the ADC nonlinearity. Just a few other things. At 356, there was what we call the zebra, and this is clean. This is due to time constant problem, and this is a two survey difference map, and you see that it has almost disappeared here. You have also the parameter for polar leakage, solar efficiency. So this is a test done on the monobolometer maps. The blue point are the point from the 2018 with ROL2. We are at this level, a red point. So it's consistent with noise estimate. The noise estimate is done by simulation. As it has been told, repeated a lot of times this morning, we need some simulation. So we made the effort of simulation, 500 full end-to-end simulation. This has been done with GenC on the oxygen machine at CNES. It is the same sky than Planck 2018 FFT10 simulation, but on the same ADC model using ROL2. What is interesting is everything is all together. So it means that the simulation has exactly the same pipeline than the data. The only difference is you point to the simulation instead of pointing to the data. Another important warning is the simulation is done with only one CMB, but it has been shown that in fact, through the SROL pipeline, you can shift the CMB at the end. The difference between two maps computed, shifting the CMB at the end or shifting the CMB at the beginning of the processing is negligible compared to the accuracy of the system. Let's go to the data. So, the end of my talk, I will, in fact, repeat what has been done on SROL1, on SROL2 maps, so on 278, on the Planck Legacy release, on the SROL2 maps. So here, you see exactly the same maps, Q and U, 100, 143, that has been cleaned by of the foreground effect. On 2018, you still see this, which is ADC, and this is 19. This is SROL2, sorry. And you see that most of the stripe has disappeared, and you start to see small structure like this. And just to give you a flavor of what we are looking for, this is a simulation. I put CMB with the same smoothing with a tau equal to 0.055. And you see that we are not far from having something at the same level. Let's go at a little bit on spectra. So this is null test. So null test, we did three different map difference. So, on the left part, you have the 2018. On the right part, you have the SROL2 result. On BB power spectrum. And you see that there are patterns like that completely disappear here. On the variance, which is here computed from the simulation, is much smaller than here. And so if we go to the BB power spectrum, that is consistent with 0, at low L, you see that, for instance, the L equal 2 was very improved by the SROL2 data, which is here. And here, you see also that we are still consistent with 0 with smaller error bars. And maybe they are even a little bit too big, and this is maybe due to the fact that we put too much of variance in the NEC-NL in our simulation. Let's go on some very interesting plot. This plot is variance computed from the simulation. So this is in multiple. This is in EE power spectrum. In red, you have the total. In blue, you have the cosmic variance, if you expect to have a tau equal to 0.055. Okay. And in green, you have the variance from the end-to-end simulation due to the noise and systematic. And when you see immediately is in fact now with SROL2 for this L, we have a lower level than the cosmic variance. So we are starting to really approaching the measure of the very low L at the cosmic variance level. Here is the power spectrum at EE. So you see very well here, for instance, that here we are consistent with almost 0, or not far from 0 with L equals 3. And now we have a real measure. And we see here that those points are much better. So let's see what happened for the likelihood. So this is the same plot that Luca shown you. So this is you remove one L, and you have on the legacy all posterior for tau. If you do this for Thrall2, you have this. So you see that what is very interesting, it becomes much more consistent. The accuracy is much better. And what is interesting is this plot is exactly what we expect, in fact. Because what you remove is you decrease the probability of having a low tau because you have a better accuracy. So if you go to the famous or infamous plot of tau evolution during age of measurement, you see that now Thrall2, this plot is done with only for low or not using T and T. You see that this tau is very consistent to the previous one because it doesn't change this value, but you improve this part because you improve the accuracy. So finally, Thrall2 get this value, and it's not far from the cosmic variance. If I remember, with this mask is 0.04. So the dataset is available here and currently available to all the collaboration members, and will be available very soon to everyone. Just one slide to tell you that this effort is not the end, and we will do Thrall2X. We have plenty of ID to improve this, and we have, I think, good ID to improve the large-scale noise. And also, we will improve, we have already tested, the component separation merge with the Thrall1. And this is very interesting because it can merge other instrument information inside the map making itself. Conclusion. Thrall2 improve, I hope I convince you that Thrall2 improve large-scale polarization, so it's a good proxy for cosmology. In the near future, there will be more release, and the idea is to release things as soon as we have a significant improvement. And this is the end, just a map. Thank you for your attention.
Thank you. Questions? If not,
it was too clear.
Very clear. Good. We will. Oh, one question over here.
What is the tau value you were expecting from this analysis?
Sorry.
What is the tau accuracy you were expecting from this?
But previous slide. I mean, for this one. So sorry. This is our way. This one, so it's 06, 05. And this will be published very soon. It's a paper from Luca. But what we expect is if we succeed to remove the last systematic, we can be almost at the cosmic variance. If.
Okay, let's thank our speaker again. And we're up. Now hear from Pavel Motlock on tensions in CMB lensing.
Good afternoon. Is the volume okay? I will assume so. All right, thank you. All right, so good afternoon, everybody. Thanks to the organizers for giving me the chance to present some of the research we put together with this amazing group of people. So we heard about the tensions in the Planck lensing data set a little bit already, so let me go into a bit more detail. As you all know, there is a CMB thing coming from Redshift 1100, and as the CMB is going through the universe, it's gravitationally attracted by all the structure in the universe in the process called gravitational lensing. And as was already said, we care about this process because it's giving us some window into the low redshift universe. So the compulsory slide of what lensing actually does, you see here there's a small patch of a sky, CMB temperature, and E and mode polarizations, assuming if there is no primordial B mode. And lensing does these tiny deflections in T and E, and it breaks the symmetry of the lensing E mode, so it generates small-scale lensing B modes. that gives us several handles how we can actually measure it in the data, either looking at the power spectra through smoothing of the peaks and T and E, or by measuring these lensing-induced B modes. We can also search for non-Gaussian signatures in the data through the process called gravitational lensing reconstruction. Now when we actually have data that's good enough to measure this effect, we can try to quantify it. And the usual way how you do it is if you have some model at the back of your mind, lambda CDM, you have a theoretical expectation for how much power there should be in the lensing potential, dependent on all your cosmological parameters. So you just introduce a new cosmological parameter, this A lens, which scales the theoretical expectation that goes into your comparison with the data. And as Anthony pointed out, there is roughly 20% more lensing through smoothing of the peaks than there should be, which is roughly 2 to 3 sigma significant. And depending on who you are, you might be a little worried or you might be not. So I don't like this A lens parameter for various reasons. One, if you introduce lensing amplitude through this way, it immediately becomes correlated with all the other cosmological parameters, which slightly complicates the interpretation. But maybe the more pressing reason is if you now want to compare lensing constraints from various experiments, each of the experiments prefers slightly different values for cosmological parameters, and so you cannot directly compare the A lens constraints from the experiments because each A lens is defined with respect to a slightly different baseline. So the most natural thing you can do is before you start your analysis, you just choose some fiducial lensing potential model and you scale this fiducial fixed model with some scaling parameter, for example, calligraphic A. Now you break these correlations, and also you have a common baseline which you can use to compare among experiments. There is one problem with this, and that is if you imagine there is some physics in the low redshift universe that is changing the lensing potential, the change can be more general than just shifting the amplitude up and down. So you would want to make sure that this one parameter description of lensing is not biasing your lensing constraints. So you can be more general, and you can scale this fiducial lensing potential by some L-dependent function of multiple parameters, which allow you to also change the shape of the lensing potential. So that's what we did. And in what follows, you can think of this θ1 parameter that will appear as changing the amplitude, with the convention that the 0 θ1 corresponds to as much lensing as you see in the fiducial model. θ1 larger than 0 is more lensing. And we also have this parameter θ2, which tells you something about the shape, about the slope of the lensing potential, with a tilde in here. All right, so now we have a description of the lensing. Let's take a look at the Planck data. We can run chains and constrain these parameters. And this is the result. So in red, you see 68% and 95% confidence limits from the smearing of the peaks in the TT power spectrum. So you see there is some constraint on the lensing amplitude, and there is essentially no constraint on the shape of the lensing potential. You can also take constraints on your standard cosmological parameters. You can make a prediction for what lambda CDM would prefer. That's shown here in this green curve. And you see that even if you allow lensing potentials that are more general than just changing the amplitude, there is still this tension between measurement and actual theoretical prediction. And so this A lens tension is not going away, even if you allow for any lensing potential. We can compare with constraints from lensing reconstruction from Planck. And as Anthony said, this tension is still in there, which means that there is no lensing potential that can actually explain this TT anomaly. And let me point out that lensing reconstruction is in perfect agreement with theoretical expectation. OK. So the Planck is not the only CMB experiment there. We can also do the same exercise with data from the South Pole telescope and their likelihood. So at the top, you see constraints on θ1 from their temperature, polarization, and lensing reconstruction. And at the bottom, for comparison, the measurements from Planck, which you saw on the previous slide, temperature and lensing reconstruction. And there are several points you can take from this plot. So one is that SPT lensing constraints are all self-consistent, and SPT consistently prefers somewhat less lensing than Planck. Second thing, you can see that the Planck TT measurement is inconsistent with all the other lensing constraints we are having at the moment. We have other constraints, for example, from ACT, but those are not sensitive yet enough, at least the published versions, to really add anything to the conversation. The reason why the SPT-TT constraint is interesting is because you could imagine that explanation of this tension is driven by some early universe physics that is changing the TT power spectrum in a way that looks like lensing. But the fact that SPT-TT constraints on lensing are actually pointing towards less lensing than the theoretical model seems to indicate that that's not the case, and early universe physics, changing the TT power spectrum doesn't seem to be the explanation of this. This is just a table quantifying the significance of the tensions between all the various combinations of the experiments. And you can see that Planck TT lensing constraints really are at above 2 sigma tension discrepant with everything else. And discrepancy with SPT polarization data actually reaching 3 sigma at the moment. If you try to do the same table with constraints on A lens, for the reasons which were discussed previously, the numbers would be biased, and you would get somewhat different numbers. Okay, so now when we pointed our finger towards Planck TT lensing constraints, let's see if we can learn anything more by slicing the Planck TT data in various ways. You can start asking, so what about what angular scales in the Planck TT data are actually driving it? And if you look at improvement in the goodness of the fit, it turns out that the lensing tension is driven mostly by these oscillatory residuals at L between 1200 and 1500. And there is also some contribution from low Ls. Once you allow lensing to do anything at once, you can shift around the cosmological parameters a little bit, and low L also drives this preference for high lensing a little bit. But that's not that interesting. Let's look into split into frequencies. So this is, again, constraints on lensing now in terms of the maybe more familiar lensing amplitude from Planck TT. And for comparison lensing reconstruction, in the Planck TT likelihood, there are 4 combinations of frequencies. There is 100 gigahertz, 143 gigahertz, and 217 gigahertz auto spectra, half mission 1 cross half mission 2, and combination of 143 and 217. So let's look at what happens if we split these into 2 halves. And we get constraints on lensing, shown here in orange and green. And it's interesting that both of these half combinations of the data prefer somewhat less lensing and less tension with the lensing reconstruction than once you combine them together. So if there was some CMB part to this tension, you wouldn't necessarily expect this behavior. And so we are still looking into this, trying to understand what exactly about the data is pushing this. And for example, how significant this effect is. Another thing you can do is you can look if there is some portion of the sky that's actually driving this tension. And for the frequency correlations, which were discussed previously, we only look at 143 gigahertz map. And shown here is the full Planck mask used that goes into the likelihood. So we started by splitting the sky into roughly 50 pixels, each of them roughly 2% of the sky. And we looked only at those pixels that have enough sky to give us some sensible constraints. In each of the pixels, we generate, using master formalism, the best fit power spectra, and then we compare the power spectra in each pixel with the power spectra from the full mask, which you saw in the previous slide. Roughly 2 years ago, there was a nice paper that Suvodeep and Ben put out, so we used their formalism to convert this difference in power spectra into difference in cosmological parameters. And so what you see in this picture here is for each of the pixels we look into, whether that given pixel prefers less lensing than the full mask, shown here in blue, or more lensing than the full masks, which would be a few of these yellowish pixels. You can notice that most of the pixels here actually prefer less lensing than the full mask. So the natural next step is to look into how does the lensing change if you combine all these 19 pixels together, and you look at what lensing amplitude does when you go from the full mask into the smaller mask, which effectively excludes some of the regions near the galactic plane. And we have some simple simulations, and we expect that just due to cosmic variance, there should be roughly 6% change in the lensing amplitude. If we actually did the exercise with the data, we see that there is a 15% drop in the lensing amplitude. So this part of the data seems to prefer something like 15% less lensing than the full 143 mask. And so this is almost all of the lensing tension. So this is very preliminary, and we need to do some tests to persuade ourselves. There is some disagreement in the first round, so I'm happy to talk about it later. And if it holds water, this might suggest that there is actually something about the foregrounds that is driving the tension. How much time left do I have? It's just 5 minutes? OK. That's more than I expected. So some people in the audience are interested in this H0 tension. So let me briefly tell you about what happens to the H0 tension if you assume that there is no new physics, and there is some systematic driving this Planck lensing tension. So at the top, you see a constraint on H0, this 67.3 kilometers per second per megaparsec from Planck TT. If you throw away the lensing information by effectively marginalizing over a lens, you see that H0 jumps up above 69, effectively reducing the tension a little bit. But once you add back Planck polarization data, the H0, which is preferred by the data, goes back below 68. All right, so in the second part of my talk, I just want to introduce this thing not many of you maybe have heard about, lensing correlations. And so lensing is this nonlinear transformation of CMB. And this lensing effect is effectively coupling CMB data at various scales. And the lensing fluctuations, which are deflecting CMB temperature and E mode, are some stochastic random field. And so effectively, this leads to some correlations in your CMB data. If you have a Gaussian unlensed CMB data, then your covariance is purely diagonal. With lensing, it's no longer the case. You can write down a simple analytical expression for how much covariance there should be. For example, here, for example, of EE power spectra between some L and L prime. And there are two basic components. There is how much stochasticity is there in the lensing, how much uncertain the power in the lenses is, and then how much your data, CLEE in this case, are sensitive to lensing. And this was tested on simulations, including when you have incomplete sky coverage, and it seems to work very well. This is the correlation matrix you get from this lensing effect. And you can see that between individual multiples, the correlation is at per mile level. However, this correlation affects a large number of multiple pairs in a coherent manner. And so overall, this effect can turn out to be significant. And effectively, what it all boils down to is this lensing covariance effect is reducing the precision or limiting the precision with which you can measure the lensing from your temperature and polarization power spectra. So for example, if we look at this tension between SPT polarization and Planck TT, then without including lensing covariance, you would evaluate the tension at 3.5 sigma, where effectively it's only 3 sigma. And as we go to better and better data, this effect will be more and more significant. So given I have time, I can actually talk about a slide which is very pleasant. So there is a similar effect called supersample lensing, supersample covariance, which arises if you have an experiment that only observes a small patch of the sky, for example, a South Pole Telescope. And what happens is now if you have a small patch experiment, you can have a lens that's bigger than your footprint. And effectively, it means that all your data is coherently magnified or demagnified by this big lens. And so effect of this lens is completely degenerate with change in the acoustic theta star, the acoustic size of your peaks. Here there is this parameter called kappa bar, which we use to describe the mean convergence in your field. And as I said, if you look at the SPT data, there's a perfect degeneracy between change in the size of the acoustic peaks and this mean convergence, shown here in blue. So in your data analysis, you can break this degeneracy because you roughly know within lambda CDM how much lensing fluctuations you would expect. And so you can put a prior on kappa bar, which allows you to measure theta star using SPT only. And effectively, what ends up happening is that your constraint on theta star is roughly 60% larger than without this supersample effect. So it's actually already important for SPT third generation. Alternatively, what you can do is you can use Planck as your external prior on what is actually the size of the acoustic peaks, which then allows you to measure the mean convergence in the SPT patch. And you find that there is some hint of underdensity in front of the SPT patch from this measurement. You can compare this with the Planck map, and it's consistent Planck map, this lensing measurement map, which we saw in the first talk, is actually consistent with there being an underdensity in the SPT patch, which in turn is again consistent with the fact that we saw less lensing in SPT data than in Planck. Okay, so these are my takeaway points. It looks like that the extra lensing in Planck TT doesn't have anything in common with an actual lensing process. There might be hints that this could be caused by galactic foregrounds. SPT is self-consistently in preference of less lensing than Planck, and starting now, these lensing-induced covariances start to matter. Thank you.
Sylvia.
Okay, so first of all, I am super happy that there are, fresh eyes looking at this. In Planck, clearly, we looked at this problem a lot. So my first comment is that when you do your per patch analysis, so you use a component separation map to do this. You use a component separated map, a CMB clean, already CMB cleaned from foregrounds. I mean, it's the SMICA map, or?
No, this is the 143 map. It's not a component clean map.
And so you need to do like the dust cleaning for each of those patches in order to get cosmological constraints, right? How do you treat the dust here?
So we assume that the power added by the dust in each of these patches is the same. So they subtract in the...
But this is wrong. This is wrong.
Okay.
Okay. Okay, so we should talk more about this.
Definitely.
And second point for the foregrounds, we did in 2015. So first of all, if it's foregrounds, you should see really different A-lands when you do the 143 alone and 217 alone. We did this. It's very similar. I mean, you showed, it's fractions of sigma moving, but it's still high from different, channels that are sensitive to dust in a really different way. Point one. Point two, at different frequencies, we use different masses, right? So we use, 70% of the sky at 143, and we use 60% of the sky at 217. And this moved from 2015. And in 2015, we also did the analysis on a 50% mask. And in all these cases, we didn't see, it's not that we didn't test it, we did tested this for 3 years. From our point of view, at least, we didn't think that this was the problem. Again, I am super happy, that you go through it, you find a clever way, and you say, it's foregrounds, guys, you didn't understand anything. I mean, the important thing is that we get to the answer.
Well, I need to add a few more things. First, what did you do for your unresolved foregrounds when you did your test before? Can you go back a few slides? Yeah, this one, yeah. What did you do about the unresolved foregrounds, the point sources and CAB, etc.?
So for this, I just used the Planck likelihood.
Yeah.
And I went into the covariance matrix and I said, these data, which correspond to
no,
the
sure,
I'm not using, I just blowed up the error bars. So the foregrounds was treated in exactly the same way as in the full.
So are you exploring the foregrounds as well?
That's correct.
Yeah, because there's a 1 sigma shift in Helens when you fix the foreground to the values for lambda CDM, because there's a small degeneracy between these Helens through NS, etc. It's a bit complicated. That's the first thing. Second thing, if you go back to the first slide, a few more slides before.
Right. So this is marginalized over foreground.
This one with the red points. Go back to the spectra residual. No, the next one. Yes, this one. So here, the regions that you highlight. So what we saw was that the Helens effect was a continuous. When you go from L1000 to all the way to 2000, the more you are adding L's, the more the Helens issue shifts high.
Yes, I actually have a slide for that.
Yeah.
Right. So
yeah. So the more you're adding it, the higher Helens grows. Yeah.
Right.
Yeah. That's the thing. And then about your dip at that you highlight in red at 1460. Yeah, this dip here. This we discussed that in the 2015 papers already.
Right.
That it's actually, we think it's actually due in part to the galaxy, because it's much higher in the 217. Well, it's much lower. Sorry, in the 217, and we played around with the 353 and the higher frequency, and it's getting deeper and deeper. So we know that there is some residual here. Right. So and yes, it's going to pull a little bit on Helens, but not that much. So it stands to reason that some of it could be due to this residual pull. Right.
Joe.
ACT will be looking at nearly half the sky, and I imagine they will be able to avoid this sampling bias you mentioned. But my question is, have you tried repeating this different patch of sky approach for the H0 discrepancy? Is there any change in inferred H0 if you divide the sky up into different
Right,
sections?
so I did, and I didn't see anything anomalous. There doesn't seem to be any patch of a sky that would be driving. But there's this issue about me not treating maybe the foregrounds correctly, so I clearly have to take a look again and make sure that everything is proper. But in the preliminary analysis doing this, I didn't see anything weird about H0.
It was also in Schwadik's paper, no? Wasn't it in your paper, guys?
Yeah, but the paper was limited to L of roughly 1300, if I remember correctly. So this is going all the way up to...
Yes.
So it seems when you exclude the galactic foreground paths, your lasing signal seems to drop a little bit. So in other words, the galactic part that possibly been contaminated by foregrounds seems to give you a higher lensing signal. So I wonder what sort of foreground physically can fake up the lensing, the CMB lensing signal. Can you comment on that?
Yeah, so as I said, this is a very, very fresh result, so we haven't had time to actually figure out what physically would be going on in there.
Any last urgent question before lunchtime? I guess not. So I'd like to thank all the speakers for this morning for staying on time. I didn't have to use the bell. Thank you. And we reconvene at 2. Do you have anything?
And I have 2 short announcements. So unless there is someone who wants to stay in the room, we will close the room if you want to leave your laptops here. But yeah, it's going to be locked until 2, so do whatever you want. Second announcement, a lot of people came to me saying that they don't have proper trousers for the dinner. So it's okay. I mean, we will, come whatever you like, I mean, try to be, nice, but if you only have shorts, come in shorts.